Där, då är vi online. Nu får jag hälsa alla välkomna till Apri 10 slutseminarium som nu är ett webbinarium. Jag hoppas att det här blir undantaget i den serie av avrapporteringar som vi har av Apris verksamhet och att vi kan träffas på samma ställe nästa gång, men det vet man aldrig. Ni som har varit med tidigare kommer nog känna igen en del av introduktionen som jag presenterar här, men jag drar den igen då för jag tycker det är viktigt att påminna om grunden för Apris verksamhet. Jag har ju varit med från början så att det blir en kort historik över Apri och svåra haverier här i kärnkraftsvärlden och en kort betraktelse om andra faror i vårt samhälle. Om vi tittar då på lite annat som händer här eller har hänt här i världen så tänkte jag börja här. En annan verksamhet. En nybyggd damm i Idaho som de stängde dammluckorna 76 fyllde upp och det gick inte så bra som ni ser. Konsekvensen av det här var bara 11 personer som dog. Men 13 000 kor drunkna. 2 mindre städer spolades bort nedströms det här dammbrottet. Och det finns mycket värre exempel på det här. 1975 så brast en damm i Kina som heter Banqiao. Och då dog 171 000 människor. Det här är en annan hemsk olycka som inträffade i Bhopal 84. 520 000 människor blev gasade. 8 000 dog under de första veckorna efter katastrofen. Och totalt sett 555 000 människor som blev exponerade för gasen. Det här skulle man ju då kunna jämföra med det som egentligen inledde det här med svåra haverier. 1979, TMI på morgonen, 28 mars. Ny anläggning, första cykeln. Där man i praktiken körde sönder reaktorn då på grund av mänskliga faktorn och bristande instrumentering. Det blev ju praktiskt taget inga konsekvenser utanför anläggningen av det här, men vi kommer tillbaka dit. Vi kan ju titta på nästa som var mycket värre då. En bra stund senare, Fukushima Daiichi. Här fick vi ju konsekvenser då för människor och miljö, men det värsta kom ju från tsunamin ändå. Tittar man på grundorsaken här så var det ju då att man inte hade tagit hänsyn till kunskap då om yttre händelser med samma sannolikhet då som inre händelser, och då gick det inte så bra. Men hur ser då våran situation ut? Jo, efter TMI så skrev man i energipropositionen 1980/81 att vi skulle kunna bemästra härdsmälteförlopp utan stora konsekvenser då för människor och miljö. Och man skrev där direkt att Barsebäck skulle ha filtrerad avlastning av inneslutningen och övriga anläggningssajter då skulle avvakta och ta erfarenheter ifrån Barsebäck. Och det gjorde man, och 1986 så kom det här regeringsbeslutet där man sa att alla anläggningar skulle hantera ett svårt haveri med härdsmälta. Och det här fortsatte ju då den forskning och utveckling då som hade påbörjats med Filtra, som avslutades med det tredje Rama-projektet 89. Rama 2 då gav oss skrubbefiltren på Ringhals, Forsmark och OKG. Men serien här avslutades med den här slutrapporten. Handbok över haveriförlopp i svenska reaktorer. Det var alltså ungefär att så här vet vi att ett svårt haveri går till. Och baserat då på det här så fanns det då några som tyckte att vi visste tillräckligt och kunde avsluta forskningen om svåra haverier. Men det drifttillstånd som vi fick allihopa när ramen var färdigt ser ut så här. Och där står det rakt av att vi ska fortlöpande följa och värdera utvecklingsarbete när det gäller då svåra haverier. Så att då när de här åsikterna togs fram att vi visste tillräckligt så bad jag min chef Emil Bachhoffner och samla ihop industriföreträdare för att vi skulle kunna gå igenom det här drifttillståndet och lyfte då fram den här texten som är skriven med rött. Och det här blev då starten på ett 2-årigt projekt som hette HAFOS, haveriforskningssamarbete då mellan industri och myndighet. Och vi följde då internationell forskning och det gav väldigt lite utväxling, så att man beslutade då sen att börja med det vi nu vet heter Apri. Och det har då fortsatt med hela serien. Den första slutrapporten kom några år efteråt, 95. Och den här sammanställningen då har jag plockat ur ett dokument som Anders Henok på Ringhals har gjort mycket förtjänstfullt, som samlar ihop egentligen allt som finns när det gäller svensk haveriforskning. Så att nu är vi här då 30 år senare och ska avsluta Apri 10. Och vi vet mycket, men vi vet också att det är mycket vi inte vet. Så får vi hoppas att det här webbinariet kommer att ge oss en fortsatt tillförsikt om att den svenska haveristrategin håller och är bra. Så att det är då min korta inledning. Då ska ni vara välkomna då till Apri 10s slutwebbinarium. Och när jag nu är färdig då så tänker jag lämna över då till Henrik Lenneskog som ska ge en överblick över Apri 10 och har jobbat mycket då för att få ihop det här webbinariet. Så att jag avslutar där. Välkomna och hoppas det kommer att bli 2 givande dagar. Tack för mig.
Tack för det, Maurits. Då ska jag ta över här. Och hoppas att ni ser min skärm just nu då. Ja, då ska jag ge en kort överblick över själva projektet här då, Apri 10. Och till att börja med vill jag säga att alla Apri-projekt drivs som 3-årsprojekt. Och då förstår ni då att det här är då Apri 10, så vi har hållit på i närmare 30 år. Och vi får nästan kalla Apri som ett löpande program nu för tiden. Där 3-årsprojekten avlöser varandra. Och de parter som ingår i Apri och som finansierar Apri, det är då SSM, det är Forsmark, Ringhals och Oskarshamn. Och varje part har representanter i en styrgrupp som styr arbetet. Och som ni kan se i de här 2 rutorna så har den styrgruppssammansättningen förändrats lite grann under Apri 10s gång här. 2018 när vi startade Apri 10 då började vi då med Maurits som ordförande. Och sen var de övriga ledamöterna Margareta Tanse-Larsson från Forsmark, Anders Henok och Staffan Dittmer från Ringhals, Patrik Isaksson från SSM och Ninos Garis från SSM. Men nu när vi skriver 2021 och vi är precis i gränslandet mellan Apri 10 och 11 så ser det ut som så här då att Patrik Isaksson, SSM, han går in som ordförande eftersom Maurits inom snart pensionerar sig. Maurits kommer då ersättas av Ola Jonsson från OKG. Margareta Tanse-Larsson har också gått i pension här alldeles nyligen och ersätts av Erik Ramenblad från Forsmark. Staffan är kvar från Ringhals, men Anders Henok går inom kort i pension och ersätts av Johan Olofsson Ringhals. Och sen har Ninos ersatts av Christian Linde på SSM under projektets gång här. Jag kommer komma tillbaka till det här lite grann allra sist i vårt webbinarium imorgon eftermiddag. För att säga ett litet tack till alla de här medlemmarna som har slutat under Apri 10 då. Sen är det jag, Henrik Lenneskog, som är projektledare. Jag tillhör Vattenfall då. Jag leder och håller samman arbetet i styrgruppen. Men de som gör det riktiga jobbet, om vi säger så, det är ju utförarna på Chalmers och KTH, våra forskare. Och därutöver har vi en hel del deltagande i internationell forskning också. Jag vill säga lite kort här om vad syftet med Apri-projekten är, och då vill jag göra det genom att beskriva det jag kallar för forsknings- och tillämpningsprocessen. Och den processen den börjar med att man i experiment studerar ett specifikt fenomen. Och man försöker därefter att tolka och analysera de experimentresultat man har kommit fram till. Därefter brukar man vanligtvis försöka göra någon slags modell av de experiment man har utfört. För att kunna beskriva observationerna. Nästa steg i den här större processen, det är att ta de här modellerna som man har utvecklat och implementera dem i en kod, en större kod som då i det här sammanhanget kan simulera hela haveriscenariot. Och då, det är koder som typ MAP, Melkor, Aztec och liknande då. Och de här koderna de behöver kontinuerligt valideras, och det gör man oftast mot större experiment, storskaliga internationella experiment. Exempel på det är Phoebus-experimenten och vi har Quench-experimenten nere i Karlsruhe, och det finns många sådana. Och när man då använder koderna, integralkoderna som man ofta kallar dem, och försöker att efterlikna de storskaliga experiment man har gjort, då kan man väldigt förenklat säga att man kommer få ett svar som är antingen ja eller nej. Det vill säga om det är ja då, men då har man fått en god överensstämmelse med det koden förutsäger och det som det här storskaliga experimentet visade. Då har man nått fram till det steget där man faktiskt kan tillämpa då kodens resultat i reaktorsäkerhetsstudierna för en enskild reaktor. Men om svaret är nej, det vill säga överensstämmelsen är inte tillräckligt god mellan kodens resultat och det de storskaliga experimenten visade, ja då får man faktiskt gå tillbaks här igen till labbet om man säger så och börja studera de här experimenten för vissa fenomen än en gång. Och så fortsätter det här kretsloppet runt på detta sättet. Och varför jag nu beskrev det här då, jo det är för att när vi pratar om Apri, då ska vi komma ihåg att Apri rör sig i det här utrymmet, den vänstra delen av flödet. I några fall genom historien har Apri även rört sig in i den här sfären där man har kunnat implementera vissa modeller i större koder. Då. Men det är viktigt att komma ihåg det här för att kunna ha rätt förväntningar på Apri-resultaten också. Man kan alltså inte ta resultat från den här delen och direkt implementera i våra reaktorsäkerhetsstudier. Då har man hoppat över det här viktiga valideringssteget. Och det är viktigt att ha med sig det. Vårt arbetssätt i projektet är som följer, nämligen det att Chalmers och KTH är de som driver forskningsarbetet. Och det är så att Chalmers har sitt fokus på haverikemi och KTH studerar mer kring härdsmältor och deras kylbarhet. Det man ofta kallar för termohydraulik kanske då. Men sen har vi den viktiga internationella biten också då. Vi dels bevakar internationella projekt i det här ämnesområdet. Och våra forskare deltar också i viss utsträckning i sådana här internationella projekt. Och sen när varje treårsprojekt når sitt slut så skrivs en slutrapport. Ni kan hitta ett utkast till denna slutrapporten på vår hemsida. Den kommer färdigställas under våren. Och dessutom avslutas varje treårsprojekt med ett slutseminarium. Normalt sett träffas vi då fysiskt och redovisar resultaten. Men den här gången blev det alltså slutwebbinarium då. Jag vill peka ut några viktiga händelser som har inträffat under de här senaste 3 åren då. Det är ett axplock helt enkelt. Dels genomförde vi 2 workshops med det här verktyget ROAM Plus som vi kommer få höra mer om sist i den här dagen. Och där hade vi vid varje tillfälle ungefär 20 deltagare från både kraftverk, från myndighet och från konsultbolag som då övade kan man säga att använda det verktyg som KTH har tagit fram för att kunna använda metodiken ROAM Plus. Vi genomförde en halvtidspresentation av vår verksamhet vid ett SSM-möte i juni 2019. Det här SSM-mötet handlade egentligen om haverihantering då, men det var ett lämpligt tillfälle att göra en liten mellanlandning och tala om var vi stod i projektet. Jag vill också lyfta fram att vi har haft en väldigt bra dialog med forskningscheferna för alla partners inför starten av Apri 11. Det vill jag särskilt tacka för. Det har varit väldigt konstruktiva dialoger där. Sen kan vi notera också att ett antal doktorander har disputerat under Apri 10-projektets gång. Det är Sergej Galushin från KTH, det är Cheng Wan från KTH också, och Peng Yu, KTH, och dessutom Fredrik Espegren på Chalmers. Och en doktorand har också lissat, det är Anna-Elina Pasi från Chalmers. Vi kommer höra nästan alla de här presentera sin forskning under de här 2 dagarna. För övrigt så vill jag då bara tala om att Apris verksamhet kommer fortsätta i Apri 11 med start redan vid årsskiftet här 2021 och som då pågår 3 år framåt och avslutas sista december 2023. Så egentligen är Apri 11 redan igång, men det kutym är att vi avrapporterar föregående projekt i början då på året när nästa projekt har startat. Några intressanta nyheter också, det är, som ni säkert har förstått, och så har vi återuppväckt vår hemsida apri.se. Vi planerar att använda den en hel del. Vi har en plan för nyhetsbrev, ni kan intresseanmäla er för det. Och vi har en ambition att öka kommunikationen mellan projekt och våra partners ännu mer under Apri 11. Då vill jag precis som Maurits än en gång hälsa er välkomna till slutwebbinariet för Apri 10. Och nu ska vi gå in på den riktiga forskningen och starta session nummer 1. Och den kommer modereras av Roberta Consilio. Vi ligger något före tid, men det tror jag inte gör någonting att vi startar upp detta. Så jag lämnar över ordet till dig här, Roberta. Varsågod.
Okay, we're gonna go forward now in the meeting. And we're gonna start with, we're gonna go listen a little bit about the research in severe accidents from NEPS. And we start with Wei Ming Ma, that will give us an overview of the severe accidents at KTH and PS, nuclear power safety. So please, Wei Ming, you have the floor.
Okay, thank you, Roberta. Can you hear me?
I can hear you.
Okay, great. So yes, my name is Wei Ming Ma. I'm going to give you an overview of severe accident research at the Nuclear Power Safety Division at KTH. Okay, so this basically introduction presentation. It's about through this presentation, I'm going to give you a bird view that will make it easier to connect the technical area, which will be presented in next presentations this morning and also tomorrow morning. Okay, so basically, here is the illustration of severe accident. So if you lose the coolant, basically the core will have heat up, the damage, and the melt will relocated into the low plenum of the reactor vessel. And in the end, if you don't have cooling, the vessel will fail, and then the melt will discharge into the cavity. So I will accelerate a little bit of the video. And finally, you're going to fill the reactor vessel, and the melt will discharge to the cavity. Yeah, so basically the research focus at KTH is on the melt progression. And the objective of research is they cool the melt, because we know if we want to terminate the accident or stabilize the chlorine, the only way is just to provide the cooling. So we have basically, so this melt progression process, we have 3 locations you can cool the melt. First is the reflooding of the damaged core. So in this core region, you can also cool the chlorine. Then in the reactor pressure vessel, you can also provide external cooling on the low head. Then in this case, you can also retain the melt in this place. We call it in-vessel melt retention. Yet finally, if you cannot do it here in the reactor cavity, you can also provide water. Basically, we can flood the cavity, so we can also stabilize the melt in the cavity. So that is basically the strategy we are using in Sweden. For example, the boiling water reactor, we are going to flood the cavity. The idea is we can fragment the melt, then form a debris bed, so we can cool it. So basically, in all previous study, in almost 3 phases, Apri, we are focused on the ex-vessel debris bed coolability and also the steam explosion. Because we know if we have such a deep water pool, we have the risk of a steam explosion. And based on our previous study, we realized this very sensitive or connect to the in-vessel phenomena actually. And we know, so if you have a massive release of melt, for example, if the diameter of the melt is larger than 200 millimeters, then in this case, so probably we can form agglomerated debris bed. This means you cannot cool it. Also, if you have a massive release of melt into the water pool, it's also challenging to have the steam exposure. So in this case, we realize it's very important for the release condition. That's why from this phase, Apri term, our research try to focus on this one. We try to look at what is the melt release condition. And basically, this is also very important to the pressurized water reactor, because for the X-vessel case, although you may have the shallow water pool, but here also depend on the melt release condition, you can cool it or not cool it. So it's very important for the X-vessel phase, we want to have the melt evolution in the low head. We call it the late phase melt current progression in the reactor pressure vessel. So basically, is first they have the core relocation into the low head, then the foam may be quenching the debris bed, then they boil off the water, and then the low melting debris will start remelting, and the oxidic debris will probably sitting in the metallic pool. And finally, at some point, you may fill the vessel, and then you may also have the melt infiltration. So all those phenomena become our focus of the Apri study. And of course, if at some moment, if you provide water, for example, from external, you may end up with this inverse melt rotation, and finally also maybe form a stratified melt pool. So this way, this all become our study focus. So look at the Apri focus I already mentioned. So we want to look at the inverse melt behavior. So basically how the base will remelting and form the melt pool, and also what is the melt failure mode, because that will decide how the melt will discharge into the X-vessel phase. So also same time we look at the base formation. We found that we don't have so much information about the metallic melt and the coolant interaction, because if you have the stratified melt pool, or if the metallic melt discharge earlier, then you probably end up with this scenario. It's the molten metallic melt and coolant interaction. And we have this long-term program, MISTI study, which is look at the physical mechanism of field coolant interaction. So right now we try to develop the facility for the prototypical material experiment, because you may all know in our study for the current behavior, we use a similar material because we are in the university, so it's difficult to operate with the prototypical material. So then we look at also the quenching of oxidation of X-vessel debris bed. So that is also the missing part in our previous study. We look at the long-term coolability, which means it's already quenched, but we have limited or little message or knowledge about quenching or the oxidation of the X-vessel debris bed. And also very important activity is try to develop model and simulation capability, so we can interpret our experiment, also try to transfer the insights or finding to the reactor application. That so this model and simulation capability is very important. So for this, we focus on this, but we also have other activity for the X immediate activity for the X-vessel phase. Meantime, we are look at a kind of alternative to the X-vessel coolability if we flood the cavity, right? So that means we look at if it's possible, we can use the external cooling of the vessel. This leverage on the EU project FVMR. So in this topic, we look at the inverse melt retention by submerging the RPV in water, also by spring cooling. So you're also going to have some achievement in the today and tomorrow's presentation. So basically, here is how we'll select the different research objective. So I already said previously we focus on X vessel steam explosion and the debris pullability. We try to look at the new limiting mechanism. Right now, we move on to the in-vessel phase, try to look at the in-vessel melt behavior. The idea is to try to look at the limiting conditions for the X-vessel melt risk. Because we know the release condition is very important for the X-vessel phase. So come to how we do this work. Here is the kind of technical approach. For the in-vessel debris behavior, we have two experiments. So basically we are doing experiment for CEMIC 2 is look at the debris dry out, melting and the melt formation. And then we also have the REM code and the missile support for the melt infiltration in the debris bed. Therefore, the melt for the vessel failure mode, we focus on the kind of development of coupling approach for thermomechanical analysis for vessel behavior. So we have both mechanistic modeling or also simplified modeling. Also, we develop creep model. And for the debris formation for the molten melt current interaction, we perform the D4M experiment. And for the MISTI, we try to upgrade the facility to perform experiment using a kind of prototypical material. In this case, we try to use the zirconium and the iron mixture in the experiment. Also, we did a study on the seawater effect on the steam explosion and quenching of particles. Also, for the quenching of the oxidation of X-vessel debris bed, here we use a kind of simulation approach. So analytical approach, we try to validate the COCOMO MEWA code and then do the React application analysis. And for development the model simulation capability, we have, for example, advanced turbulence model for melt flow heat transfer. We also use the direct numerical simulation. Also, we develop a surrogate model for quick estimate debris bed coolability. And we try to also implement kind of coupling approach. Basically, it's like COCOMO real-life coupling or COCOMO MELCO and COCOMO surrogate coupling for different applications. Finally, come to the alternative to X-vessel coolability. We do this feasibility study of the vessel melt retention for the Swedish boiling water reactor. Here we do the advanced structural modeling of the reactor vessel or with external cooling. Also did the experiment for the spring cooling capability. So let's end with my presentation. And this Apri research is, of course, mainly supported by Apri. Then we also have co-funding from SSM, also have the EU, NC, the Swedish Nuclear Authority, NKS, also the Japanese Nuclear Authority support. So thank you for your attention.
Thank you, Wei-Ming, for the comprehensive view of the ongoing NPS research on severe accidents. Are there any questions for Wei-Ming? Remember, you can write on the chat on the YouTube. Okay, so I guess there are no questions for Wei-Ming. I was just wondering, the investor retention research, it is coupled to a EU research effort, like you showed you in your last slide. Is a project ongoing in EU EVRM?
EVRM, yeah.
Yes, okay. And NQS, it's just a side question. NQS which project is related to, is being funded by NCOS?
Yes. What is the name? It's finished in 2018 or 19, I think. Let's see.
Okay.
What is the name? Sorry. Okay. It's not
No worries
all
about it.
three.
That's just
finished.
to be a side question.
Because you
But I
probably
guess-
know we have to apply every year. So we succeeded, I think, first year or second year. I have to check it.
I have one question for you, Wei Ming, from
Please.
that I can read in the chat. The question is, which aspect of it would you say, of the research, would you say are unique in an international perspective?
You mean our KTH research?
Yes.
This research topic we are choosing actually, for example, melt to remelting and behavior in the lowerhead. I think is something is missing in the even at the international arena. So also the melt, like a metallic melt and coolant interaction. Previously, they are more focused on the jet fragmentation, but not on the debris bed formation. So we start kind of scopy study. We did just 5 tests, and we found quite different characteristics from oxidic material. So I think that is also something different. Also, come back to the MISTI experiment. It's also mechanism study. So right now we are using is also the zirconium iron mixture experiment. So it's also quite unique, I think. That is what from the unique part of our research, I think. So that basically the topic we choose is not because it's important for our Swedish severe accident management strategy, or it's also important for the severe accident knowledge internationally, I think.
Okay, thank you. I mean, I guess we're going to hear more details about the NPS research on severe accident. But we will take a 10 minutes break right now, and we will start again at 9:50.
Okay, thanks.
Okay. Hi everyone, welcome back from our pause for our break. Now we would like to welcome Andrei Komlev. He's going to talk about SIMECO 2 research on debris and melt pool. Andrei, you have the floor. Oh, yes. Just to remind you, if you want to write a message in the chat, you should go to the home page on the Apri.se. There is a small place that is written chat. You can click there and then you can write any questions when Andrei finishes presentation. So, Andrei, you have the floor, please.
Yes, thank you, Roberta. Thank you. Good morning. My name is Andrei Komlev. I would like to, on the behalf of group of authors, I would like to present NPS activity devoted to the SIMECO 2 research on debris remelting and melt pool convection. So this is the contents of my presentation. I will shortly inform you about the motivation of study this phenomena. Then I will maybe more details talk about SIMECO 2 facility concept and some technical details. And then I will go to the our preparation for the experimental study of debris remelting and dry out in SIMECO 2 facility. So as you know, and as was detailed mentioned by Professor Ma, during this severe accident of light water reactor, the core material melt down and relocate in the lower plenum, forming a debris bed. Then, due to decay heat, debris can start to melt and basically forming metallic melt because of lower melting point of metallic part of debris and oxidic part. After that, in a late phase of severe accident, basically for the specific case of in-vessel melt retention, stratified molten pool can be formed with typical structure of stratified layer with top metallic layer and oxidic layer because of density differences. This mentioned phenomena like debris remelting, melt pool formation, and heat transfer in the lower plenum provides the condition for the determining thermomechanical load on the lower head of wall and structure. So this evolution of in-vessel debris bed play important role in the severe accident progression, including vessel failure mode and melt discharge upon the vessel failure. So in our division regarding SIMECO 2, we have two parallel experimental activities. The first one is multi-component debris study dry out and remelting. Here we can consider, because this is quite a complicated process, including many different phenomena. We can consider dry condition, remelting in dry condition. We can consider wet condition, also melt formation and relocation, boiling, dry out, coolant infiltration. And after that, as I mentioned, the debris, the corium debris includes two main components: fusible metallic part and refractory oxidic part. In the late phase, if in-vessel melt retention strategy is applied, these two components can remelt and forming stratified molten pool. Important research task for this both phenomena is dry out, is a study of dry out, melt formation and relocation, the dynamics of multi-component debris remelting to the molten pool, and some specific phenomena related to the heat transfer in molten pool, like focusing effect, inversion layer, influence of the interfacial crust between top metallic layer and bottom oxidic layer. So the study of this phenomena can give us important information about vessel failure mode, which is quite important for the developing new model for the severe accident progression, as well as validation of existing model and codes. So experimental study of natural melt pool convection was started in our division more than 20 years ago, when original SIMECO facility was developed by Professor Segal. So, and that facility was devoted basically for the study of heat transfer in molten pool, in single layer and two layer. So currently we're developing a new experimental facility called SIMECO 2, which was originally designed to study heat transfer of stratified molten pool, but also due to design of the facility, it can also be used for the study of debris, dryout and remelting, as will be shown later in my presentation. So regarding study of natural convection, you can see in the slides, so despite a number of experimental programs were devoted to study natural convection, and you can see the main research facility, there are still lack of data basically for the obtaining of correlation for the stratified molten pool, effect of top layer thickness called focusing effect, and effect of top cooling of metal layer, which this phenomena are quite important, as I said, for the code validation and model development. So maybe more details about SIMECO facility to give you an understanding. So main concept of test section design. So SIMECO facility has a hemispherical slice geometry with radius of 500 millimeter and width about 120 millimeter. The unique feature of this facility is using of contactless method of induction heating to have a minimal impact on the processes which can place in the molten pool or debris heat of debris remelting during heating. So then also unique feature is using of novel temperature measurement system, including optic fiber, which is not affected by induction heating. The visual transparent quartz wall to have a possibility of observation of the phenomena inside the molten pool and debris, and a special simulant material which will be used in the experiment for the different simulant material for the debris dryout study and molten pool heat transfer as refractory heat generating oxidic layer, steel particles in case of debris dryout study, and special salt system as fusible metallic part, tin particles for the dryout study, and again, low dense metallic system which can form immiscible to liquid stratified pool. Due to safety reason, the SIMECO 2 facility will be is located actually in the protective containment, and includes following main parts. Of course, this is a test section and induction heating system, including the high frequency generator, which can provide the power output power up to 150 kilowatt, electrical connection, and the slice section itself. Here you can see the picture of installed slice section. So system for the melt preparation, melt transfer melt preparation and transfer to the test section, which includes two separate independent tanks for the metallic melt and salt melt preparation, and also the new central cooling of test of facility. So as I mentioned, that one of the features of the facility is using of induction heating method. This method was selected to minimize the impact of the heating process on the processes inside the molten pool and debris bed. So the main part of this induction system is inductor. So and also the electrical parameters of the system. That was electrical parameters such as voltage, current, and frequency were selected based on the pre-test simulation, which I showed next slide, and also based on like technical reason, possibility of visual observation. That's why inductor has a special windows for visual observation. And also the induction heating system includes top and bottom electromagnetic screens to protect metallic layer and steel vessel against heating. So that's the first time when induction heating is used for the heating of molten pool in slice geometry, basically for the salt layer. So due to this reason, that was quite challenging to select the proper design of inductor and screens to provide uniform heat power distribution in the salt pool. So to reach the purpose, the calculation was done using one force of facility because of because of complexity of system for the computational simulation. So in the center of slide, you can see the results of volumetric current density distribution, and still you can see some skin effect in the salt layer, but combined with natural convection, which will be in real experiment, we are expecting the quite uniform heat distribution during experiment. That's also like was shown in previous experimental program, that induction heating can provide heat distribution close to the volumetric one, like in a real situation. And also the challenge for us is to quantify power distribution during experiment, because only in that case, if we can quantify it properly, we can use this for the model validation as input parameter of heat distribution. The next important part for us is temperature measurement system. Basically, that will be provided by using of advanced temperature techniques based on the optic fiber with Bragg's gratings. This we're going to use two types of fiber. The first one is encapsulated by stainless steel tube, which will be located in the inner and outer surface of the cooled vessel to get data for the temperature distribution and then calculate it and then use it for the calculation of heat flux distribution along the polar angle. And the second type is optic fiber encapsulated by quartz glass to completely exclude any metallic parts. This type of fiber will be used to measure temperature inside the pool. So this, as I mentioned, this type of fiber is not affected by induction heating, and we can, it's quite important for this type of experiment, and we can get the temperature, realistic temperature data inside the pool. So the same techniques will be used for the debris remelting and dry-out experiment. So, and experiment for the melt pool convection is still under preparation. And now maybe more details will talk about our activity for the experimental study of debris dry-out and remelting. So the same facility will be used but instead of molten pool and like salt simulant, here will be particular debris will be packed in the test section and inductively heating. So as I mentioned, the prototypic corium includes two main components: the fusible material and refractory material. This is the same principle we will use in our simulant material. The first part of simulant is tin, as a representative of fusible material, basically a mixture of uranium, iron and zirconium. And the second part, stainless steel particles, which represents a refractory oxidic part of corium, basically uranium and zirconium oxide in solid solution. So ratio between these two materials was selected based on the results taken from the Melcore simulation of PWR, and so the current ratio 45 by 55% mass percent was selected. Of course, we have not only like requirements for the composition taken from the prototypic material, but of course we have some technical requirements for the experiment, such as to have a minimal porosity of debris bed to reduce necessary power for them to reach debris dry out and remelting. And of course, we have like a limitation of our power supply. So based on all of these requirements, the special particle size was selected of tin and stainless steel spheres. Based on this particles, mixture was prepared, and porosity was experimentally measured. And then this mixture was packed in the facility. So these parameters such as porosity, average particle size, composition were used for the pretest simulation of dry out, which was done using COCOMO code, and condition, initial and boundary condition, you can see in the right part of slide. Condition for the debris, boundary condition from bed walls, and properties of simulant material. Based on the compromise between computation time and accuracy of simulation, the necessary meshing of system was selected. And next slide, you can see the results which were obtained. So I'm showing only the final results, the final cases. Cases number 1, 2, and 6. In these cases, dry out was not reached because of lower input power. Case number 7 requires more power than actually we would like to have because of some safety margin. But cases number 3, 4, and 5, this is acceptable for us because of reaching of dry out and acceptable power. So I would like to mention that in this cases 3, 4, and 5, the artificial top layer of glass particles were used to reduce necessary power and to artificially limited the water access to the heated debris bed. So in the left corner you can see the location of the dry out, and in the particular metallic debris, and this results we were using for the preparation of the measurement devices to find the proper location. So this experiment is still under preparation, but I think we will manage to perform the experiment soon. So, and as a summary, I would like to mention that we did some we did some development of SEMECO2 facility, which can be used for the 2 types of experiment: dry out, remelting of debris, and then formation and heat transfer and natural convection study in molten pool. And for this 2 tests, this experimental activities under preparation. Regarding debris beds, dry out and remelting, SEMECO2 program will be focused on the complex phenomena mentioned in the slide. This is molten material remelting, penetration into oxidic debris, dynamic of multi-component debris remelting to the molten pool, heat transfer of debris of solid or molten pool to the vessel wall and penetration, and effect of physical chemical interaction of debris behavior. It's like our future activity. So that's all. I'd like to thank you for your attention.
Thank you, Andrei, for a very nice and comprehensive presentation. Thank you for keeping the time. Now I have some questions, but before that, I was asked for you to turn off the presentation mode, so we can then ask questions for you. Okay. So I hope you could hear me. Can you hear me?
Yeah, I can hear.
Okay, hi, Andrei. It's a little bit of a delay, so I'll try to speak a little bit slower. We have a question from Henrik Lanniskog. Yes. He was wondering that the ratio between the fissile and refractory materials were chosen from Melcore runs for BWRs, and then the natural question would be, how much of the ratios differ from PWR conditions, from BWR to PWR conditions, the ratio between the debris and melt in a Melcore calculation?
the current ratio we use is 45% of fusible material. As I remember, for the PWR, the fusible material will be a little bit less, less than 45%.
But once if you're going to develop any modeling, then later on this could be taken into consideration.
But of course, yeah, of course, that's also we to have the exact ratio for the experimental program. When we go to the PWR condition, we will do the special simulation for this experiment. Yeah.
Okay, we still have time for one more question.
Hello.
Hi, it's like I can see that Andrei is speaking, but I cannot hear him. Yeah.
I'll speak.
Okay, so just one more question. We have time for 2 more questions. I'll have one for myself. It's like one of the things you're looking at is like porous media and then remelting of this metallic layer who then will penetrate in the porous media because the stainless steel will not melt in the experiments. It will be just thin. So are the results comparable or will be correlated to the results in MISPOD?
Yeah, sure. That's so currently, as my colleague will present in MISPOD, they study the melt in infiltration. So currently they use already molten material. In SIMECO 2, we will consider the early phase when a material is solid and then remelting. So that's like a sequence of experimental program. One is complementary to another one.
Mm-hmm. We have 2 minutes and one more question from Henrik Glenskog. He wonders if, because he uses slice setup, it's very efficient and you can have nice visualization and control. But what kind of boundary effects do you have to take into account with this setup? Would you have like a wall effect or some like bypasses because of the wall issues between the wall and the material, or other issues that could come up from a slice setup from boundary effects?
Well, of course, we like in all facilities, we will have some artificial effect, basically related to the heat losses from the front and back wall. Maybe this is like one of the important artificial effect of our facility, and basically for the facility with slice geometry. Because in reality, it's quite hard to provide adiabatic condition for the front and back wall, where if you want to have like good visualization, if you use the transparent walls.
Okay. In a nutshell, if you could say in very few words, because we're going to cut for the next presenters, just take so many questions. But Padre Kisakson was wondering in a very short way if you could say what's the difference between the new SIMECO and the old SIMECO. What's unique about the setup compared to the early SIMECO?
Well, unique feature. The first one, of course, is the induction heating, the contactless method of heating. The second one is the simulant material. In new SIMECO, in new SIMECO, we we're going to use the top metal layer, which has direct contact with the bottom layer, and also it has higher thermal conductivity, which was not done in previous experiment. That's actually quite important to study focusing effect.
Thank you, Andrei.
Like
Thank you very much for your presentation and answering all these questions. We have to move on, but I believe that if anybody has other questions, you can write it and I can send to Andrei and he can answer you afterwards. Thank you. Peng Yu, I think we should start with your presentation now. Are you there?
Yes, yes. Hello.
Hello. Hi, welcome, Peng Yu. Peng Yu is going to present a couple thermomechanical approaches for reactor pressure vessel failure analysis. So, Peng Yu, you have the floor.
Thank you, Roberta. Hello, everyone. Yes, I'm Peng Yu, and the title of my presentation is the coupled thermomechanical approaches for the RPV failure analysis. My presentation will consist of 4 parts. First, I will introduce the motivation and the objectives of this work. Then I'll present you a mechanistic coupled thermomechanical approach for this RPV failure analysis. Then we will introduce a simplified approach for the efficient analysis. And finally, we will give the summary and outlook. As we all know that the severe accident mitigation strategy adopted in the Nordic BWR is a kind of the ex-vessel corium retention strategy. The idea is that when the corium is released from the RPV, it will pour into a deep water pool and is expected to fragment, quench, and form a coolable debris bed in this deep water pool. The ex-vessel analysis, such as the FCI, MCCI, and melt coolability, are essentially relying on the RPV failure mode, like the failure time, rupture size, and the location, as well as the amount and the superheat of corium and available for the release. So this study focuses on the RPV failure analysis. In the RPV failure phenomenon, it is a transient thermal fluid structure coupled problem because it involves the multiple heat transfer inside the vessel and the mechanical behavior of the RPV. Then we would also expect that the natural convection would be highly turbulent in this corium, and the structural behavior would also be highly nonlinear and temperature dependent. Also, we would expect a significant creep deformation under such high temperature and stress load. So the objectives of this work is to develop new approaches and models for the coupled program and the involved phenomena. In this work, we generally propose the 2 approaches for modeling this phenomena. One is the mechanistic approach, which we will employ the CFD and for the molten pool heat transfer and the FEM for the structural behavior of the RPV. In this work, we propose a 3-stage creep model, and we also compare the volume load transfer and the surface load transfer regarding the load transfer in this coupling treatment. Then we propose a simplified efficient approach where we use lumped pyramid model and couple it to the FEM solvers. Then here we develop a lumped pyramid code called trans IVR, and then we couple it to the FEM code ANSYS mechanical. Generally, in the mechanistic CFD and FEM coupling approach, we would address 3 important issues. The first one is the multiple heat transfer, then is the RPV mechanical behavior, then is the coupling between the interaction between these 2 mechanisms. In the mechanistic approach, we would use the ANSYS front to deal with the first issue, and then the ANSYS mechanical to deal with the second issue. And then we would transfer the transient thermal rows to model the interaction between these two terms. In this approach, we generally assume that the influence of vessel deformation on the multiple heat transfer could be ignored in order to simplify this problem. The feature of this coupling approach is that it will support the transient analysis, the complex geometry. This feature would enable us to simulate problems like we would include the penetrations of the lower head in the future to make the simulation easier. And we would expect reduce the user effort, and it supports the advanced models. Then there would be two ways for the transient row transfer, because generally in the multiple heat transfer, we would solve the heat transfer problem between the fluid and the structure, which means the column and the RPV. Then the structure behavior is affected by the thermal behavior of this structure. So basically, if we adopt the volume load mapping, then the thermal volume load of the structure part would be transferred to the mechanical analysis. Then we would perform standalone structure analysis in this RPV failure. And for the transient surface load mapping treatment, we only map the thermal information of the boundaries on this mechanical problem. Then we would solve this problem as a thermal structure, the coupled problem. Then for these two approaches, we do simulations against the forever EC2 experiment to validate these two treatments. The forever experiments theory was conducted in KTH on the molten pore heat transfer and the RPV failure. It is a 1 to 10 scale geometry, and in this specific facility, the RPV steel 16M95 was employed for the lower head, and the binary salt was employed as a simulant for the corium. We can see a schematic of this experiment, and then this is a GIF of this experiment. Here we developed a new creep model called the modified theta projection model for the creep behavior of the steel. It describes the three-stage creep behavior process, and it is temperature and stress dependent, and the time hardening and the strain hardening models are supported. These figures compares the model prediction against the experiment of the creep. In this experiment, this figure shows the temperature snapshots at different times. We can see that generally the temperature increased with time until it reached a steady state, and we can also see the clear thermal stratification, which is an expected phenomena in the natural convection. This figure shows the temperature along this polar angle. We can also see this profile increased with time until it reached a steady state. And generally, when it reached the steady state, it agreed well with the experiment, which is shown as the dot points. Here we give results on the mechanical analysis. Generally, in the simulations, if we use the VLM and SLM treatments, both approaches would predict close results, which are also agreed well with the experimental data. This figure shows the creep strain field at the failure time. We can see that the maximum value of the creep occurred at the location where the high thermal load was observed. And the maximum creep strain was also close to each other, as shown the values here. This figure shows the wall thickness changes along the polar angle, and we can see that the we would expect the maximum wall thinning at the high angle position, and both the VLM and SM treatments agreed with the experimental measurements. Then we apply these approaches to the BWR case. We assume that this case would form a 1.9 meters homogeneous cooling pool in the lower head, and we have in-vessel water cooling and a volumetric heat of 1.1 megawatts per cubic meter in the column. And to simplify this problem, we don't consider the penetrations. This figure shows the temperature that evolved with time. We can see that it generally increased with time because we don't have X-vessel cooling. In the mechanical analysis, both approaches predict quite close failure time, as shown here. And these two figures shows the development of the maximum creep strain and the total deformation of this bottom point. Generally, we can see that both of these two trends shows that the deformation developed quite slowly at the beginning, then it accelerates after some point, and the results between these two treatments are great with each other. So we would also like to compare the computational efficiency between these two approaches, these two treatments. We can see that in the forever simulation, this SLM method employed twice the core numbers, and it used slightly longer time than this treatment. And in the BWR case, this method employed the same core numbers, but cost quite a longer time than the VLM. So we can conclude that the VLM treatment, which is this one, would be more efficient than the SL treatment. Then after this work, we would also want to develop a simplified, efficient coupled approach. The idea is that we want to replace the modeling of the molten pool heat transfer with a lumped parameter code and then couple it to the FEM. The advantage would be that the lumped parameter code would be more efficient than the CFD and also than the PECM. And for this approach, we can also be able to model the detailed mechanical analysis of RPV, like we work with ablations. So such treatment would be quite attractive for studies that are mainly focused on the mechanistic modeling of the RPV structural behavior. In this part, our task is to develop the code, the coupling of the code to the FFEM code, and then the verification and validation of these two parts. The trans-IVR code, here we show the schematic of the model. The general features include the transient analysis of the molten pool heat transfer, then both one layer and two layer molten pool configuration. Also, the RPV heat transfer can be modeled as 1D or 2D problems. We support the crust formation, the calculation of the wall thickness, and we also support arbitrary boundary conditions. Regarding the coupling, we would employ the VLM treatment. So basically, the transient thermal loss from this part would be transferred in the mechanical analysis. And after that, I would additionally note that there would be a detailed study focusing on the RPV failure of an ablate RPV work by my colleague Hongdi Wang after this presentation. So after the development of the approach, the first part is to verify the development of the code. Here we use benchmark case called the UCSB FIBS benchmark. In this part is to verify the model performance on the two-layer pool heat transfer. And we will use the resources from the US DOE and the US Idaho lab reports for comparison purpose. In this calculation, we compare the heat flux distribution, cluster thickness distribution, and the wall thickness distribution. Then we can see that in the oxide part, it agreed well with both two results. And in the metal layer part, it lies somewhere in between these two predictions. In the second case, we want to validate this code to confirm that it is able to model the transient for heat transfer. So in this problem, we choose a live 7-way experiment conducted from the German KIT. In this experiment, the transient, the heating power changes with time from 29 kilowatts to 9 kilowatts. Here we selected the experimental data and the simulation data using relapse SCADAP data for comparison purpose. In this part, we compare the energy split of the cooling pole upward to the surface and downward to the vessel. We can see that at the first 3 stages, it agreed with the relapse data, and in the third stage, generally, it predicts better data than the relapse code. Then we compare the heat flux profile along the polar angle, which would be a key parameter we would like to compare for the vessel load. We can see that the relapse SCADAP data showed quite flat distribution, while our data agreed better with the experiment. There is the Forever EC2 experiment. We want to validate the coupled simplified approach. Here we would employ the experimental data and our simulation results using the mechanistic CFD and the FEM approach for comparison purpose. First, we compare the bulk temperature using the trans IVR with the maximum temperature and average temperature in the CFD. Generally, we can see that the temperature increased with time until it reached a steady state, and the value agreed with the maximum value of the CFD. We would consider it a reasonable prediction as a lumped parameter code. Here we compare the temperature distribution along the power angle. This curve shows the prediction of the trans IVR, the code, and it also agreed well with the experimental data. In this animation, we show the thermal distribution of the vessel. Now it's visualized in the ANSYS mechanical, which also indicates that the necessary information was properly transferred to this code. And in this figure, we show the wall thickness changes at the failure time. It also predict the profile of this shape, and the maximum wall changes was also occurred at this position, which is a reasonable prediction. So summary is in this work, we proposed two coupled approaches for the RPV failure analysis. In the mechanistic approach, we coupled the CFD and FEM analysis for the RPV failure analysis, and then we calculate the Forever experiment and then apply this method to a BWR case. We compare the VLM and SLM methods, and more computational efficiency was seen in the VLM treatment. Then we developed the lumped parameter code trans-IVR for the calculation of transient heat transfer, and a simplified coupling approach was developed based on this lumped parameter code. Then we also did the validation and the verification process. The outlook as follows. Then the first one is the extension of the modeling capability of the RPV failure. The main purpose is to that we would like to capture more on the history, the location, and the failure mode. Then in the future work, we may consider the RPV rupture, then as well as the detailed modeling of the penetration failures, and also maybe we'll do more on the post-certification process. Also, further code development could be done for this RPV structure behavior in the future. Okay, that's all for my presentation. Thank you.
Thank you, Pengyu. We'll open the floor for questions. Like we did before, could you please stop sharing your presentation so we can have less delay? But can you hear me?
Yes, yes.
Okay. If there are some questions here. One is from Henrik Gleneskog, trying to read this. So his question is that the use of lump parameter code plus FEM is said to be more efficient than a CFD and PCM. Are there any disadvantages by not using CFD, PCM, and similar codes?
Yes, because the lump parameter code it has more assumptions because then we would expect the configurations same as in the IVR strategy, we may have the stratified pool and or homogeneous pool, but then in the Nordic BWR case, it would be slightly, the phenomena would be slightly more complex. Then in future, more features should be added to be able to cope with such a distribution. Yeah.
Thank you. We have more time. That's amazing. I have a question for you. It seems that the trans EVR underpredicts the wall thickness change. If you look in the slide, in the slide it shows that it matches the experiment on the front wall thickness, but not on the maximum wall deformation on the back, left, and right sides. But it's still, even though trans EVR underpredicts the wall thickness change, still the failure time agrees well with the experiment. Why is that?
Because after some stage we can expect that the deformation would become quite drastic. So even a slight difference in the prediction of the failure time, then basically the profile would change quite much. So in future it would be also a good idea to investigate what kind of failure criteria could be chosen, because if we check the Merkle code or something, they also provide different failure criteria. If we use different criteria, then we would also expect the different then the failure time matters.
Thank you. Are there any questions from anyone? If not, I have another one. If I could ask one more question before our break. You mentioned in the beginning of the presentation that the material properties have a non-linear characteristic. Is that taken into account in the trans EVR?
Yes, because currently it was only considered in the structure part, like the creep behavior and also the plastic deformation. So if we use trans-IVR, we're still using the same models in the structure analysis part. So, yeah.
Okay.
Yeah.
Thank you, thank you. If there are any more questions, I could write them down and then send to Pengyu so he could answer later on. Believe it or not, we're ahead of schedule. We should have a break now, 10 minutes break. So Henrik, please do tell me if we should take this break, we should make a 10 minutes break, or if we should make a 15 minutes break.
Let's make a 15 minutes break and we come back at 11 o'clock.
Okay, so thank you again, Pengyu and Andre, for the presentations. We'll take a break and we'll be back at 11 o'clock. Thank you. See you soon.
Thank you. Thank you.
10.
Hi, everyone. Welcome back to our seminar. Everybody hears me well, hopefully. We would like to continue our presentations. We will start now with Hongdi Wang. He will present his work on advanced structural modeling of reactor pressure vessel wall with external cooling. Hongwon, you can now share your contents and the floor is yours.
Yeah. So, hello everyone, I'm Hongdi. It is my great honor to give the presentation here. My topic today is the advanced structural modeling of a reactor pressure vessel wall with the external cooling. There are 4 parts in the presentation. Firstly, I will introduce the motivation, and after that, I will introduce the methodology and the validation of the material models, and then analysis result of the reactor application will be introduced. The last part, it is the summary and the outlook. In the Fukushima disaster, the meltdown accident will lead to the damage of the corresponding reactor pressure vessel. So the vessel integrity is very important in the nuclear power safety requirements and gain a lot of attention after that. In the meltdown accident, the vessel will be threatened by a wide range of behaviors, including the vessel deformation and the vessel wall thinning and even the melt through. So the vessel integrity should be investigated in depth. Usually, the failure model and the failure time and the failure location are regarded as the key points and will play an important role in the external vessel activities during the accident progression. However, in the calculation analysis, we usually face several difficulties or issues, and we have to consider them and to solve them. Firstly, it is the failure criteria. How could we judge that the vessel will fail in the numerical study? And secondly, due to the presence of the high temperature inside the vessel surface, some local material will be melted down to create a unique vessel profile. So even after setting the failure criteria, the failure model and the failure time of the vessel is different, and the different vessel profile, and as well as the different applied loadings. So a methodology is necessary to assess the vessel behaviors in the accident scenario. In this study, a methodology is established to address the issues on whether that the vessel integrity could be maintained when the lower head of the vessel is suffered the given conditions. To achieve that aim, firstly, we should have a good understanding of the thermomechanical behaviors of the vessel, and then set a failure criteria. And after that, the computational approach of one-way coupling from Melco to ANSYS was established. And finally, we used the computational approach and the methodology to investigate the vessel behavior in the reactor applications. In the meltdown accident, the vessel will suffer continuous mechanical loading and thermal loading. The internal pressure and the external pressure and the relocated column and the vessel gravity is the source of the mechanical loading. And the heat flux, the internal temperature and the external temperature will be transferred into the thermal loading on the surface of the vessel. And the vessel will be response the above loadings with the stress and the strain behaviors. Actually, in the numerical calculation, the stress and the strain state of the vessel is multi-axial. And here we just use the one-dimensional formula to make it more easier to be understand. The stress, it is the physical value that express the internal force between the particles, and it is the applied force on the material divided by the cross-sectional area. And the strain, it is the deformation of the material results from the applied stress. The strain, it is the sum of the elastic strain, plastic strain, and the creep strain. It should be mentioned that the creep strain, it is the permanent deformation, and it will occur when the material suffers very high temperature. And to investigate the failure mode and the failure time appropriately, we should set the failure criteria. In this study, we considered two kinds of failure criteria. The first one, it is the ultimate stress failure criterion. It is the maximum stress that a given material can withstand under applied force, which is the material property. And then we compared the one minus stress of the vessel with the ultimate stress to judge if the vessel will fail. The ultimate stress failure criterion, it is a quite common failure criteria in the engineering practice. However, in the reactor analysis, the temperature is very high, so the creep strain cannot be ignored. It will play an important role in the scenario progression. So here we use the second failure criterion, the creep strain based failure criterion. The creep strain will have 3 stages. Considering the previous research in the literature, we think that the primary stage and the secondary stage, we regard these 2 stages as the reliability predicted. So the start of the third stage is 20% creep strain. In this study, we use the 20% creep strain as the creep strain limited of the vessel behavior. And here is the computational approach. We combined the advantage of the Melco and the ANSYS APDL code and to investigate the vessel behavior. In the Melco, the whole power plant was modeled and the accident progression was simulated to obtain the information that the ANSYS need. And then we transfer this information to ANSYS to investigate the structural behaviors of the vessel detailing. In the computational approach, there are 4 steps. Firstly, we should collect the material properties and then develop the material models. After the validation of the material model, we use it in the reactor applications. Now I will introduce the step one by one. The step 1, here is the example of the material properties of 16MND5. All the materials properties are temperature dependent. And step 2, we should develop the material models in ANSYS. Here, the creep strain and the elastic plastic strain are separately calculated in ANSYS using the modified time hardening model option and the nonlinear isotropic hardening model option in ANSYS. These 2 figures, they are the fitting curves of the material model. And we also compared our material model with other models, and the material model shows a good performance here. To further assess the material model performance, we use the validations. We validate these material models against the existing experiments. Currently, we developed the material model of 2 materials. The first one is the SA533B1 material. The second one is 16MND5 materials. These 2 figures, they are the examples of the validation of the material model SA533B1. Now we use 2 assessment factors to assess the material model. The first one, it is the absolute differences in creep strain between the numerical results and the experimental result. And the second factor, it is the root mean square error. We use these two assessment factors to judge our material model, and the model shows a good performance. And after validating the material models, we use the methodology and material model in the reactor applications, a type of Nordic BWR. In this reactor application, two scenarios was considered, and external cooling is considered too. In the Melco, the whole power plant was simulated, and here the vessel was simplified as a 2D asymmetrical geometry with the vertical part and a hemispherical lower height. And here the lower height failure is activated and the penetration failure is deactivated. There are three meshing configurations in Melco: the core mesh, medial mesh, and the finer mesh. And two scenarios was considered. So totally there were 6 cases in the ANSYS to investigate. In Melco, because the high temperature, because of the high temperature inside the vessel surface, so some location of the vessel will be ablated and forming the ablation inside the vessel. And then we developed the corresponding ablated profile in ANSYS, and also transfer the temperature, the pressure, and other information from the Melco, transfer them into the corresponding boundary conditions in ANSYS and to study the vessel behaviors. Actually, the whole power plant was simulated in Melco for 9 days. And from the first line figures, we see that the structural behaviors of the vessel during the second stage and the late stage is expected to be stable compared with the first stage, since the thermomechanical loadings in these fingers are significantly lower in the second stage and the late stage. So considering the computational cost in ANSYS, we just use the 12 hours as the running time and the observation time to investigate the vessel behavior in ANSYS. This is the temperature profile, and this is the mass evaluation. From these two figures, we see that the Melco output data with different meshing configuration have non-negligible differences. So it is necessary to study 6 cases using different meshing in ANSYS. Okay, now let's show some analysis results from ANSYS. This is the stress profile, and considering the all cases, we could get the conclusion that the maximum stress is in the range from 218 ampere to 241 ampere, and they all occurs near the outer surface of the vessel lower height. And this figure, we compared the stress state of the vessel with the ultimate stress. The sufficient margin indicates that the vessel wall can maintain the structural integrity when we consider the stress-based failure criterion. This is the Cripps chain results from ANSYS. And from the first figure, we see that the Cripps chain in the inner region of the vessel lower height is more significant than in the outer region due to the high temperature in internal surface of the vessel. And from this figure, we see that the Cripps chain contribute most to the total strain, and both the Cripps chain and the total strain, they all sufficiently below the 20%. So this result indicates that the vessel can maintain the structural integrity with the IVR cooling. And here, it is the deformation of the vessel in the ansys. From the first picture, we see that the largest deformation occurs in the location with the larger ablation. And in this figure, we see that the larger displacement of the vessel is consisting of the maximum vertical displacement and relatively larger the maximum displacement is consistent with the maximum horizontal displacement and a relatively larger vertical displacement. And for this part, this vertical part of the vessel without a relocated column, we see that the horizontal displacement is dominant due to the internal pressure in the vessel. Okay, from the above Nordic BWR case, we displace the vessel behavior detailedly under the given conditions. Now let's focus on the geometric discontinuity. In the case of Nordic BWR, the high temperature from the molten column may exceed the melting temperature of the vessel steel and forming the ablation inside the vessel. And in other case, the heat transfer from the molten pool to the vessel may concentrate in the top layer and forming the ablation as well. So from these two cases, we could know that usually this column-vessel interaction can lead to some local material melting and forming one ablations or many ablations of the vessel inner surface. So it is necessary to study the vessel behavior given the residual thickness. However, the geometry discontinuity of the residual thickness will lead to the stress concentration. So what is the stress concentration? It is a location in an object where the stress is significantly greater than the surrounding region due to the irregular geometry and the irregular material. And it usually occurs in the holes, grooves, and fillets. From these three figures, we see that the stress in these special locations are much higher than the surrounding stress. So usually if the shape of this special location is practical, the design should be optimized to improve the stability of the structure. But if the shape is hypothetical, for example, in our case, actually the fillet shape is assumed in our case. So we have to investigate the effect of the fillets and try to reduce the effect of the fillets. There are two methods to reduce the effect of the stress concentration. The first one is to increase the element size, and the second one is to increase the fillet size. After choosing the appropriate meshing, now let's focus on the fillet size effect on the vessel behavior. Because the Nordic BWR has many ablations with many fillets, which is not easy to study the effect of the fillet, we adopt the conditions in a benchmark. It is a simplified scenario, and also the vessel will be simplified as 2D geometry with the vertical part and the lower part. And this is the mechanical loadings. This is the thermal loadings. In this case, we will study the effect of the fillets on the vessel behavior. After developing and validating the material model, we study the effect of the fillets. We considered 4 kinds of fillet radius: 0 mm, 1 mm, 4 mm, and 12 mm. And we studied the vessel behaviors at the failure time in each case. We see that they have similar behaviors with different levels of fillet radius. And then we study the creep string distribution. They also have a similar creep string distribution, but they will fail at the later time with the increase of the fillet radius. The figures, we could see it more clearly that the failure time shows a trend of roughly linear increase. And then we set the observation time as longer time. And we observe the vessel behaviors with the 72 hours. And here we count the minimum internal pressure resulting to the vessel field as the failure internal pressure. Namely, when the fillet radius is 4 millimeters, the failure internal pressure is 41 bar, and when the fillet radius is 1 millimeter, the failure internal pressure is 40.5 bar. So in this case, we see that there is no significant differences in failure internal pressure among different fillet levels, but there is also a significant effect on the failure time. And then we continue to increase the fillet radius to a larger one, and also consider to smooth the conjunction between the ablation part and the part without ablation, and similar results could be found in this case. Here is summary. In this study, a methodology to assess the mechanical and thermal behaviors of the ablated vessel wall was developed, and the validations of the models against the existing experiments were also performed. And we also use this methodology and the material model to investigate the vessel behavior in a reactor application, the Nordic BWR, and have some analysis results and conclusions. And also we continue to study the effect of the geometry discontinuity and to provide insights on the effect of the failures on the vessel behaviors, and got some conclusions. And in the near future, the same methodology can also be implemented on the assessment of an ablated vessel without IVR. And the more sensitivity analysis on other parameters can also be performed. And then the rupture dynamic using Lestiner is also planned, as well as the influence of the penetration on vessel behaviors. Also, that's all. Thank you very much.
Thank you, Young-Won. Yeah, now I open the floor for questions. We have some already in the chat. I'll start with a question from Henrik Landeskog. If it's okay with you, I don't know if you can hear me well.
Yeah, I could hear you.
Yes, and like we did before, just stop sharing the presentation so we can.
Okay.
Yes, so it'll be easier for us.
Okay.
The first question from Henrik Landeskog is that reactor pressure vessel has different materials, and there was a lot of talk about that, and somewhat they differ when it comes to, for example, different carbon contents in the vessel wall or the vessel itself. So the question is the effect of the material properties on the models that you have used. Do you foresee any differences in the results? And then if that's inside your model, if you take into consideration the different materials of the reactor vessel?
Currently, we use two kinds of material. However, when we investigate the vessel behavior of different material, the boundary condition, I mean the mechanical and the thermal loadings are also different. So actually, we could see some differences between different material, but currently we cannot make sure if it is results from the material property or from the applied loadings. So if we want to compare the differences between different material, maybe later we have to apply the same loadings on the vessel behavior and control other factors and to see the effect of the material property.
Thank you. Sergei Galushin has also a question. He wondered, what do you think about the effect of reactor pressure vessels support skirt on the stress distribution across the lower head?
Sorry, you mean the internal pressure effect on the lower head compared with the vertical part?
The stress distribution across the lower head because of the support skirt in the reactor vessel.
You mean the stress distribution among the lower head, the effect?
Yeah, the stress distribution across the lower head, because there is a support skirt in the reactor pressure vessel.
The internal pressure, it is one source of the mechanical loading, and but at the lower head, it is also contain the gravity of the relocated column. So in the lower head, the distribution, it is much higher than the vertical part because it is not just from the internal pressure, it also just from the loadings from the gravity of the relocated. So in the vertical part, actually, it is just the internal pressure loadings, but in the lower head, it is suffered from the internal pressure and the gravity of the relocated column. So in the lower head, the stress, it is much larger. But I'm not sure. Did I address it very clearly?
Sergei, you can absolutely. Oh, you know, you cannot. But if you have some other question, please, you can send it again if you're happy with the answer. And in the meantime, I'll ask you another question. Thank you, Jan. Again, I have a question related to this external cooling of the reactor vessel. I just wonder, how is that considered? Because in our SAMGs for both Forsmark, and I can also say from Oskarshamn side, because we were developing the new SAMGs, we do not fill up. I would understand that you're considering this external vessel cooling by means of filling up the containment with water. Is that what you mean about the external
yes.
Cooling of the reactor vessel?
Yes, now we study the vessel behavior, want to confirm the vessel mode and the vessel failure, mode and the vessel failure timing. We just want to provide the insights on the external vessel activities, because the timing and the mode, it is very important on the external vessel cooling. I agree with you. It is related to the activity of the containment. So when we define the vessel failure behavior, it is maybe more useful for the activities of the containment.
Yes, I just want to keep in mind, we do not fill up the containment to cool the reactor from outside. We use the system to actually as a spray, and we end up filling up the containment as a consequence. And it takes a long time, and we would not be able to fill up the containment before vessel failure in a SBO. So you should be maybe careful with how this cooling assumption, it cannot be realized by containment flooding. So I think you should be careful with this containment cooling and maybe review your Melkor model, because we would not be able to cool the reactor from outside, not by means of flooding the containment. And this is not the intention either, not from the new guidelines and not even for the old guidelines. Plus, even if that was the case, we would never be able to fill up the containment in time before the vessel failure. So
yes,
this is
I
just
understand.
observation.
Yeah, because currently we just developed the methodology of the investigation on the vessel behavior, and it can also use on the case without the external cooling. And later on, we will did more analysis on that kind of case. Yeah.
And so I'm just trying to. That's going to be good to have a good communication with the power plants, to understand how their severe accident management guidelines, because that would change and how you're modeling this scenario in a Melkor. So that's why I'm just putting a seed here that you cannot. This is not foreseen in our SMGs to think about cooling the reactor tank by filling up the containment. But thank you very much, Wang Li. If there are more questions, I can see that you can see some comments on the right side in the chats as well. Some of them are questions, some of them are comments. We cannot go through everything, but you can absolutely look on the right side and see other questions that will be interesting to address. Thank you very much again, and then we can move on to Yang Xiang. Yang Xiang, are you there? Can you hear me?
Yeah. Can you hear me?
Huh. Yes, I do. Hello. Yang Xiang is going to present for us the scoping test of debris formation with metallic melt. So you have the floor.
Okay, thank you. Hello, everyone. My name is Yan Xiang. Today, it's my honor to give this presentation. So my presentation is scoping test of the debris formation with metallic melt. My presentation includes 6 parts: motivation, test facility description, effect of melt superheats, effect of water subcooling, and some comparison with of the particle size and porosity, and lastly, it's the conclusion and outlook. So as we were known, in severe accidents, as the pressure vessel fails, the melt in the low hand is discharged into the dry well. This dry well is filled with the water. So it's in BWR, this dry well is deep water pool. So and the field will have strong interaction and heat transfer with the water. So the debris formation in this process, we for a debris for this debris coolability is very important. So our D4M project is motivated to investigate the characteristics of a debris bed from the metal-rich Korean coolant interactions. Different from the previous D4 research, which used the oxidic melts, because most of our tests in the reference, we just based on oxidic melts, but in our Melkor simulation, in the reference that we get large amounts of metallic melts in the low hand, and we also get different kinds of debris beds, like the cake formation and the particle debris in the oxidic melt test. So it is necessary to have a test with metallic melts to investigate the debris formation. And here is the review of the metal water system. So we can see that most of the test is based on the wood metal. This wood metal is a low melt points metal. So it is the metal, the fuel water interaction is different from the prototypical type in the nuclear power plant. So, And here, most of the phenomenon also focus on jet breakup. And also that's most of these tests, it's a small scale test and the melt mass is lower than 1 kilogram. So for our D4M tests can make contribution to the understanding of the underlying mechanism with the mechanic melts in its interaction with water. Based on high temperature melts, tin and medium or larger scale tests, especially for the debris formation. And this is our D4M experiment setup. We use the simulate materials is tin, and the tin was propelled in the funnels with the induction heater. After this induction, the melt temperature reach the target temperature. The melt will deliver to these funnels. Funnel, we applied cross to get a uniform jet and coherent jet. And the melt will discharge into this water pool. And this water pool is 1.5 meter. And the melt will finally reach the bottom catcher. And this catcher is 0.5 multiplying 0.5 meter. And we also have several cameras and high-speed cameras to record the fragmentation and debris formation phenomenon. And after each test, we get the particle size distribution and the porosity. So because porosity is a very important property of the debris bed. And for this property measurements, we have several kinds of porosity. Firstly is the close porosity. This means that we have some particles that is hollow, but water cannot penetrate inside. And this porosity was measured by this market water tank by the density mass and the volume of the water. So we can get the close porosity. And for open porosity, it means that the water can penetrate inside in the debris beds. And this porosity is the total porosity minus the close porosity. For total porosity, we get from a scanning laser scanning system here. We have 3 scan laser, and we get the X, Y, Z value of this debris bed. So we can get the total volume, and the porosity can be the total porosity can be obtained by the density mass and the volume. And this is a test matrix, and we have 5 tests: the HL, ML, LL, MH, and MM. This means the HL means that the high superheats and the lower water subcooling. And this test, we have the same melt jet diameter, 20 millimeter, and the same jet free fall height, 0.23 meter. And the difference between these tests is just the melt superheats and the water subcooling. And we just have one test that have agglomeration in a high superheat and a lower subcooling case. And this will show 2 typical tests of the strong fragmentation test in the high superheat and the lower subcooling case. And we also have a frozen jets in the medium superheat and the high subcooling case. And if you mention that we record this test is about 120 frames per second. We also applied a grid, the background grid, to get the velocity of these jets. And for this strong fragmentation case, we have at the initial time, the pouring is just, we just have some droplets, but we have the coherent jets at the third picture. So after that, we have a strong heat transfer and evaporation. And we also have in this frozen jet case, we have a coherent jet at the third picture here. After the melt pouring in this jet, in the bottom pour, the jet was fast to cool down. And so it's have solids. And then we can see here it has a frozen jet. And now I will show you the effect of the melt superheats. And this is 3 video at almost the same subcooling, but have different water superheats. The first one is 114 degree. This one is 82 degree, and this one is the superheat is 50 degree. So we can see here for the high subcooling test, high superheat test, we get after the particle reach the bottom catcher, the strong heat transfer and the evaporation can be seen. And this lower superheat test, the particles have been cooled down in the following process, and we can see the particles, the debris beds, and it also have some evaporation, but it's not very strong in this high subcooling case. And after all of these particles reach the bottom catcher, so we can see that we still have a strong evaporation, and the particles seems to merge together to form agglomeration. But this in the lower subcooling superheat case is just the particle debris bed. And this I will show the temperature history. This one is the temperature in the final nozzle after in the nozzle in pouring. This is the releasing time period. So we can see that's different superheats in the nozzle. And this is the temperature in bottom catcher we get. So this is the releasing time. Here, after that, for the high superheat case, we have a long time to quench. But at this medium and lower superheat case, quench time is much it's shorter. So the melt temperature of the case, high superheat and the low subcooling in the final is much higher than those of the case, medium superheat and low subcooling, and the low superheat and low subcooling, resulting significantly higher temperature of debris bed in the bottom catcher. So consequently, the debris bed in the case, HL leads to considerable period to be quenched at the bottom. This is because of the particles of also, while the debris particles of case ML and LL are already quenched during the falling process. This also can be seen in videos. And this is our debris bed characteristics. So the first is the whole view of this debris, 3-case debris beds, and this is the cross section. And this is some particles of morphology. So first we can see that from this debris bed, this is just a large cake, and this is the particle debris bed. And from this, the cross section we get from this is agglomeration, and we can see some cavities in this cake, but it's not so much. So this can be defined as the can be an example of the closed porosity. And here we have the particles debris bed for the cross section. We can find that small particles at the bottom and the large particles at the top. This also seen the same trend. And now I list the same size of the particles, 11.2 millimeter and 9 millimeter. So we can find for these particles, in the high superheat case, the particles is smooth, but in these two tests, the particles, the surface is considerably rough. And we can get also from some information with the laser scanning system, we can get the total porosity, and also we get the debris bed angle. So we defined that the angle about the bottom line and the incline line of the debris bed. So we can get the maximal height, this one, of the debris bed, and we also can get the total porosity from the scanning system, and we can also use the market water tank to get the close porosity, and we also measure the angle of this debris bed from different sides and get an average angle. So we can find that for the maximal height, as the superheat decrease, the maximal height increase, and for the total porosity also show the same trend. But for close porosity, we don't find too much difference. At this one is 7%, this one is 40%, and this is 10%. So it's just for close porosity is around 10%. And for open porosity, this is the important for our water penetrating inside to cool the debris bed. So this open porosity is 5%, 57%, and 69%. So as the superheat decrease, the open porosity increase, and also show the same trend of the average average angle of the debris bed. And this is the particle size distribution of these three cases. It is to lead to indicate that in this high superheat case, we have agglomeration. So exclude this agglomeration, we get the particle size distribution. So in this case, the average diameter is 6.9 millimeter, and this one is 9.1 millimeter, and in a low superheat case, it's 10.3 millimeter diameter. So I compiled these three cases, exclude agglomeration. So we can find that for the high superheat, it can have a smaller particle size, and this means that we have a strong fragmentation in the following size process. And last, I will show the effect of the water subcooling. And this is the three videos at a case at almost the same superheat and different subcooling. So this is the water temperature is 90 degree, and 70 degree of the water, and this is 50 degree of the water tank. So we can see here for the lower subcooling tank, we have particles, and for the medium subcooling case, we also have found some larger particles and like some big chunks. But in the in the high subcooling case, we just have frozen jets. So it also can show here is the temperature history in the final nozzle. We have almost the same performance in final nozzle, but we have different water subcooling. So at the similar melt superheat, water subcooling has a significant effect on the melt solidification. And debris particles in this case are quenched during the falling process because we don't have some particle temperature higher than the saturated water, 100 degree. And this is the debris beds we got obtained from these three cases. And it's also the same whole view of these debris beds, the cross section, and some particle morphology. So from this, at the lower superheat case, at the lower subcooling case, we have particles like this. But at the high subcooling case, we just have the frozen jets. And you also can show in the cross section. And for particles, we in the lower subcooling case, we have particles. And in this medium subcooling case, we have the big chunks is much larger than 10 centimeter. So Also here we have the frozen jets, and from these frozen jets we can see the instability performance. And this is the particle size distribution. So because of we have frozen jets in the high subcooling case, so we don't obtain some particle size distribution in this case. And for these two cases, in the lower subcooling case, we have the average diameter of the particle is 10.3 millimeter, and in the median subcooling case, the average diameter is larger than 16 millimeters. So also we have for subcooling, you also have a significant effect on the particle size. So of these 5 tests, we have the morphology of these debris particles. So the morphology of debris particles change significantly with the water subcooling and melt superheat. So in the high superheat and the low subcooling case, we get a smooth, solid particle. And in the lower superheat and the lower subcooling case, here we obtain the rough, solid particles. And in the medium superheat and the lower subcooling case, we can see that we have some hollow and porous particles. And in the low superheat and the high subcooling case, we also get some flakes. And in the medium superheat and the high subcooling case, we get some chunks. So based on all of these 5 tests, we get based on the reference, we can analyze the condition of these 5 tests, and we can get based on the reference, we can get the interface temperature with the melt temperature and water temperature. And this line is the TH1, it means the homogeneous nuclear temperature. So nucleation temperature, and this blue or green line is the minimum field boiling temperature. So, and this pink zoom is the thermal interaction zoom. It is most possible to have steam explosion. So so based on this analysis, we have no steam explosion. This is agreed to our observation. We don't have steam explosion in our test. And I also compile our porosity to, this is the total porosity, to our previous D4A test from D4A 10 to 25. And D4A test was based on oxidic melts. So all of those at 1.5 meter, this is our bottom catcher. So most of the previous D4A tests, the porosity is in the range of 40 to 60. But our porosity in the case at high superheat and low subcooling case, it's much lower than our oxidic melts due to the agglomeration. But and while the porosity in the case at medium superheat and low subcooling and low superheat and low subcooling, it's almost 70. It's higher than that we get from the oxidic melt test. And I also compile the particle size to the D4A test and also the follow test with the prototypical melt test. So this size distribution are different from those of the D4A, which is used the oxidic melts, and the follow, which is used the prototype oxidic melts. So with large particles in the D4M. So I also to analyze the possible dominant fragmentation mechanism. So we have 3 series of the instability. So about KH instability and RT instability, and also the critical Weber-Lumber criteria. So as we assume that these wavelengths of also the critical diameter as the surrounding or water and steam was corresponding to the 50% of the cumulative particle mass. We can see here these points are the serious critical wavelengths or critical diameter. So we can find that the KH instability wavelengths, the diameter as the surrounding steam is corresponding to our median diameter. So for this analysis, we can find that KH instability may dominate the fragmentation. And this is the conclusions. A scoping study on debris beds formation from metallic melt coolant interaction has been carried out in the D4M facility. And we have some observations. No steam explosion is observed. And melt superheat and coolant subcooling has strong effects in debris beds formation. And compared with the oxidic melts, the botanic melts shows a higher tendency to agglomerate, which may hide the debris bed's coability. And the Korean risk assessments should consider the different features of debris bed with melt-rich or oxidant-rich corium. And this is for in the future, we will do more systematical tasks required to with the current simulated team to build a database of metallic melts, jet fragmentation, and the resulting debris bed characteristics. And also, because the team temperature, the melt temperature is just 230 degrees, but it is far from our oxidic melts. So we will use more higher melt point simulates of the zirconia and iron mixture should be used to reduce the property gap between the simulant and the prototypical material. And also we will do some models and numerical simulation with like Fluent or Kokomo codes to have some analysis. Okay, that's all. Thank you.
Thank you, Yangsheng. We open the floor for questions. We already have some. Do you hear me well? Yangsheng, can you hear me?
Yeah.
Okay.
Okay.
Yeah. So, let's go for the questions. Thank you for your presentation. Let me see. Henry Glenniscook has a question. It seems that the high subcooling results in efficient quenching, but when the debris freezes in the way we see in the video, would that make long-term cooling more difficult due to this morphology?
For frozen jets, because we have also we have frozen jets. It's very large. It's we can because the particles just some strip from the frozen jet, so it's just some flakes, and we get obtained small parts of these particles. But in the frozen jet case, so we don't analyze the particle size.
I'm talking about, I'm probably not in the cases that we have a cake that is just the ones that freezes beforehand, but it has this little long string. So I didn't quite get it. Sorry. Would that influence the long-term cooling? Would it make it more difficult with this morphology that you observed?
Yes. Yeah, for the agglomeration, it's very difficult to have cool for the long cooling. The coolability of this agglomeration is very difficult. But for particles size, this type of debris is okay because we have a larger porosity and the water can penetrate inside to cool the debris. Yeah.
So are there any differences in morphology of the debris particles? Because you talk about the size distribution and you compare to the oxidic material and the metallic material, but are there any differences in morphology of the debris particle when compared to the tests in oxidic material?
In metallic melts, the surface of the particles seems to more smooth, and we have flakes, particles. Flakes is a thin like a slice, but in previous oxidic melts, we don't find this phenomenon. It's just some rolls or some like more spherical particles. We don't have this slice of flake particles.
Okay.
So this is different. Yeah.
But the oxidic material, they can also have you can also see the same effect of subcooling and melt superheat in the morphology, that changes with the subcooling and the morphology as well, right?
Yeah. We can also see this. The effect of the subcooling and the superheat also have the effect on the oxidizing melts particles.
Okay, we have some. If I have other questions, so I see some, I can send you and then by email. Thank you for your presentation again, and thank you every presenter for holding time. Believe it or not, I think it's the first time in Apri that we are on time. So then we deserve lunch. We'll take a break for lunch. It will be from 12 to 1, and then we start again, but then we're going to hear about Chalmers. So thank you.
Okay.
Bye-bye. Henrik, you would like to say anything you know about the next step? We all go for lunch.
Yeah, we all go for lunch, and we will meet again at 1 o'clock for session number 2. So bye-bye for now.
Bye-bye for now. Thank you. Bye.
då önskar jag er välkomna tillbaka till session 2 som vi ska hålla på med nu i drygt en timme. Så hoppas att lunchen var trevlig. Jag heter Mattias Olsson och jobbar som radiokemispecialist på Forsmark och har varit doktorand tidigare på Chalmers, avdelningen för kärnkemi, som ska stå för presentationerna i den här sessionen. Och först ut alldeles strax har vi Christian Ekberg. Och om du vill börja dela din presentation genast när du hör det här, så kanske jag kan hålla råda i 30 sekunder till, för det är ungefär så lång fördröjning vi har mellan att jag säger någonting och motsvarande sak visar sig på YouTube. Och den här sessionen kommer att handla om kemin i samband med svåra haverier. Och först ut som sagt är Christian Ekberg från Chalmers som ska ge oss ett litet retrospektiv över haverikemiverksamheterna som har försiggått på Chalmers de senaste decennierna. Och Christian är professor i kärnkemi och dessutom i industriell materialåtervinning. Och eftersom vi har en del engelsktalande med oss, så resten av sakerna jag kommer att säga under sessionen will be in English. So I will now leave the floor to you, Christian.
Tackar så mycket. Ska jag hålla på engelska eller svenska? Jag försökte prata tidigare. Hör ni mig överhuvudtaget? För Mattias hörde mig inte tidigare när jag försökte berätta att jag delade min skärm. Hör du mig, Mattias? Hör någon mig? Ser ni mig? Tidigare när jag försökte berätta att jag delade min skärm.
Jag hör dig nu, Christian, men du kommer inte höra mig förrän om 30 sekunder.
Nej, okej.
Vi ser dig och vi hör dig, så det är bara att köra.
Okay, hopefully it will work. I never got the instructions whether or not to speak in English or in Swedish. I thought it was Swedish, but then Matthias now said the rest will be in English, so it will be in English, at least the slides, and I will be sort of English. So welcome to this presentation by what has been done at Chalmers. We will start with a bit of history, what we have done over the years with the different eras, and it's quite important here, I think, to stress that the major work, or the majority of the work being done in any project, I would say many these days, is usually done by PhD students, at least when there are such people present. And therefore we have divided I have divided the presentation into the different eras for different PhD students. This said, we have also ongoing work, of course, but this is presented by the active PhD students. That would be Anna-Helena Pasi. And we have also a presentation by Fredrik, who just finished. And he also got his little era thing here, but he will give much more detail later about his specific work. So, in the beginning was our late professor Jan Liljensin. He started this work quite early, and actually just now had a discussion with Vano about iodine and potential hazards of that just this morning. And in 1985, he, together with Oliver Lindquist studied the cable pyrolysis and saw that it had a profound effect on the pH of the water phase that would be in the release of hydrochloric acid. And then also they saw that there would be several other components. For example, there would be organics that would be released, and we saw different effects there in the 80s and 90s. A Rama report in 1989, for example, as you see pointed out here. In 1995, we had a PhD student, Richard Malmbeck, who placed mixer settlers in Forsmark to try to investigate the content of iodine by solvent extraction in the water phase online. and there was a licentiate thesis presented on the topic. In 99, or actually a little bit earlier, I did some modeling with respect to iodine, or iodide in air and water. This was a complete failure. I presented results in Finland and I was far out from everything else. Although I was using the up-to-date databases, showing that, well, since there was quite simple calculations using the program Freak, there were no real mistakes in the calculations, but the data itself was a problem, which was highlighted actually by accident, maybe I would say just a few years ago, but probably more than 10 years ago, when Joachim Holm made his work and I did some simulations. And we noticed that the 3 iodide species had a stability constant which was out by 48 orders of magnitude. And that's in the database. And that's a little bit worrying for modeling, of course. So we focus more on experimental work than modeling actually these days, or actually since a long time. So we have Henrik Lenneskog, who was the first serious, I would say, PhD student working on this work. And he was also fully funded from Apri. And he built a dedicated mock-up of a BVR and studied the distribution of iodine between the air and water phase as a function of different parameters in the water. And then Joel retires already in 2003, and Lembit Siever took over, but Joel is in principle still the intellectual leader because he's the one who actually knew something about it. And the absorption of I2 and methyl iodide under severe reactor accident conditions was also studied with respect to metals. Siever moved to physics in 2004, and in 2005 there was a more detailed study on the absorption of the water phase by these iodide species. And then radiolysis was added also in 2005, and Henrik defends his thesis, iodine metal surfaces interactions under severe accident conditions in a nuclear power plant. And you can see there the conclusions, but we saw that copper did some actually complexation with the iodide, with I2. And then Joachim Holm started in 2006, also with combined funding from SKC and Apri, and in some special cases also from NKS. And I became the formal group leader, but then Henrik and Joel was essentially the scientific references in the group, as Henrik still is to a large extent. The experimental setup was upgraded. We decided that the work done by Henrik, which means when he got some sort of card, the data chip card with a couple of cables and good luck from Joel, was not really working well because it was too much work to get it working. So we bought a detector system and then started to look at the distribution of ruthenium on different metals in the containment, for example. And the NROI collaboration with VTT started in 2008, and the VTT collaboration has been ongoing essentially since then to increase the knowledge on radiolytic oxidation and also the effect of aerosols, typically. Jocke defended his licentiate in 2009, but then he was snatched by industry in 2011 before finishing, unfortunately, which we still hope he will do. 2008, Sabrina started to work, and then she was typically working with iodine. This was, I would say, the fundamental iodine work when we talk about organic iodides. The supervisor was then, of course, Mark Foreman, because we deal with organics, Henrik, and me. And there was a significant amount of experimental work, and it was ahead, typically, of the current work, and then produced within the BIP project. So when visiting the BIP meetings, we saw that the work that was suggested we already did. And we also saw that also the French company was also doing these investigations on a much more expensive scale, but still a little bit after and coming to essentially the same results. We continue to work with VTT, and we have now the comprehensive thesis, the chemistry of organic iodides under severe nuclear reactor accident conditions in light water reactors in 2015. And she has moved around, and she was lastly seen at PSI in Switzerland, but I think right now she moved back a little bit to Berlin. I'm not mistaken. Maybe she's back in Sweden. The idea of her thesis was quite good because it actually took the whole series. We can see here the reactor itself, and starting from the formation of the organic iodides to the partitioning between the gaseous and aqueous phase, and then the hydrolysis reactions, radiolysis reactions in the aqueous phase, radiolysis in the gaseous phase, and then the surface interactions with painted surfaces, non-painted surfaces, then potential the filtration in the scrubber system, and then finally the potential releases to the environment. So this was from cradle to grave with the organic iodides, which has been quite well refereed, I would say. Then Ivan Kayan started in 2011 with a focus typically on ruthenium. We saw from Joachim's work that ruthenium was a bit of a bugger. It stuck to everything. It reduced the ruthenium oxide and then it stuck to everything. So now we start to see, can there be some effect of the interactions between ruthenium and iodide? We saw the revaporization of ruthenium, which was clearly induced by gamma radiation. We also looked a bit at the transport of ruthenium in the reactor cooling system and the importance of air radiolysis products, or of course then typically nitrogen, N2. And we saw some interactions with cesium iodide and a possible oxyhalide formation here. The collaboration with VTT was deepened. There was a significant mutual knowledge transfer, and we could go much further on to these formations of aerosols and the reactions, especially with cesium iodide. He defended his thesis in 2016 and is still working in Switzerland for another couple of months, but I will come back to that. Then we had one of our first postdocs, Emma Conti. She started in 2018, and now we have a modeler. She is actually a physicist, which we don't have very many of in the chemistry department. But this was a big plus for us, I would say, because now we started to have somebody in the group speaking the modeler's language and speaking the physics language in this case. Again, it was Henrik and me who were typically supporting as much as we could in different areas, and we started with the Melkor simulations for the position of iodide with different metals. And we could see that there were simulations of the experimental work of interactions of iodine. This work essentially did by Henrik long time ago when the world was young. This has now been simulated quite efficiently, and we think we can understand it. So we can also see here that she made a mock-up of the experimental facility that Henrik built up once. And there was then the implementation of the COSIS code for severe accident analysis. And to build this model, we saw that of Nordic BVR based on the Melkor containment model as we had at that time. And she was hired at OKG, which I will come back to a little bit later, but she will stay. And then the last and the freshest PhD we have is Fredrik Espegren. Starting in 2015, he will then work on tellurium, which we moved away from iodine because it was seen that the work that was done on iodine, finishing with Sabrina, essentially put us where the forefront was. We could, of course, do more experiments, but we have answered essentially the questions that we felt we could answer from a reactor perspective and the reactor containment perspective and interaction perspective. So we went on to other elements, as you could see, ruthenium, tellurium, and then stretching into several different areas. Again, it was Mark, Henrik, and me trying to sort out the supervision. But of course, being a PhD student in this group means that you often supervise more or less yourself. We are there as discussion partners. We are a little bit allergic to telling somebody what to do. So that means that, as you will see later, they come out, the PhD students, with a large amount of ability to control or to steer or to plan themselves. So what Fredrik did, he will discuss in much more detail later, so I will not spend too much time on it here. But he looked at the chemical interaction between sea salt and tellurium, seeing that when cooling with seawater, we may have an increased source term for certain elements. And this has also been seen for, I think it was niobium in the Fukushima. We have seen some volatilization, typically chlorides, and chloride volatilization is not uncommon in the high temperature chemistry at all. And we could also see the tellurium deposits during a severe nuclear accident. And in 2020, he defended his work. You can see the long title there. And he stayed at Chalmers for a short while to work with teaching. So what is the industrial relevance of the work we have done here? Well, we can see here what happened to our former PhD students and postdocs. Well, Henrik at Vattenfall, Jocke at Vattenfall, Sabrina, several postdocs, right now probably in Berlin. Ivan is at PSI, although his position finishes now, so he will look for probably a position at the Joint Research Center. Emma will go to Oskarshamn, and Fredrik is currently being interviewed for industrial positions. I will not go into any details there. Fredrik can do it if he wants to later, if he has any updates. So I would say that the work that's being done, even though the details of the scientific findings may not be immediately industrially relevant and applied by industry, we can see that the people working with this topic and also performing the actual experiments and getting an understanding of the questions of relevance for industry are then the real product of our work, I would say, in this case. So what will happen in the future? Well, we have now Anna. She will present her work. She already presented her licentiate thesis on tellurium behavior and management in the liquid phases in the containment during a severe nuclear reactor accident. We will recruit a new PhD student to go alongside Anna in February. Again, will be me and Mark, typically, being the former supervisor at Chalmers, but we hope to keep Henrik as a mentor for this work from an external point of view. And again, the main collaborator for the future will be VTT. We have a good relation with the Finns and a good collaboration in general, so we'd like to really continue that. And it also increases, I would say, the impact of the work we do. We have just recently done a work together also with the Czech and the Norwegians on irradiations and on ruthenium and iodine chemistry. Thank you very much for your attention, and now we'll go into much more scientific detail, looking at the presentations by Anna and Fredrik. Thank you.
Thank you, Christian, for your introduction and for all the PhDs you keep producing for the industry. We have use for them. According to our chairman, Henrik, the questions can be handled in both English and Swedish. And our chairman has also asked a question that we can see in the chat. Så frågan från Henrik som han har skickat in här, det är: hur löser ni att införskaffa den ibland väldigt dyra analysutrustningen som ofta krävs för den här typen av experiment?
Det är ju en väldigt bra fråga och tyvärr en väldigt svår. Den är väldigt lätt att fråga. Vi försöker ju hitta det billigt och begagnat naturligtvis som vi kan. Det finns ju inga finansieringskällor för detta egentligen för den här typen som då inom akademin kallas för medeldyr utrustning, vilket för en liten avdelning blir en svindyr utrustning. Men den är inte på nivå med en nationell resurs. Det är ju de svindyra utrustningarna. Så att nej, det är svårt. Vi får hålla oss till de kemidelar vi har, och jag skulle vilja säga att en större frågeställning än just hur vi får råd att köpa det är hur hittar vi kompetensen för att göra det vi behöver göra. Den utrustning som Henrik gjorde i början på 2000-talet, då fanns det glasblåsare som man kunde komma över och man kunde diskutera med hur man kunde göra utrustningen. Att bara hitta en glasblåsare idag är en ganska komplicerad fråga. Inte enbart ekonomiskt utan även rent praktiskt.
Tack så mycket. We should not fall behind the schedule, so we'll move on to Fredrik Espegren and the next subject. And as we've already heard, Fredrik defended his thesis last year on nuclear accident chemistry of tellurium. And he will give us a talk about his subject now. So I hope you're with us, Fredrik. You can start sharing and move ahead.
Yes, I am. Thank you for that. Let's Let's see. I think it should be shared now. Okay, so I need that. Okay, I will. Wait, are you seeing? What are you seeing?
It's a bit of a screen fuck up. We only see the presentation mode. Your presenter mode, sorry.
Okay, that was new to me. Oh, wait.
Look better for a short while.
Let's see this. Now.
That's not too bad. That's good. Except that I think we can know. Now you see your presenter.
Okay. Okay, hi. So I will start now. Sorry for that. My name is Fredrik, and I will present some of the work I've been doing at Chalmers during the last few years. My topic, as Christian hinted on, is tellurium, and I will focus on three main topics here: seawater, cesium iodide, and metallic surfaces. These were sort of the main focus of my work. But I will start first with some introduction. And a lot of my research is based on the Fukushima, or in some way correlated to it. And as you all know, it occurred in 2011. Essentially, the combined effect of an earthquake and a tsunami causing damage to the site. I will not go into great detail into this, but I want to show you sort of the releases and give some example of that. And we can start out with the tellurium, specifically 132. And here you see a map over the Fukushima prefecture, over the estimated release of tellurium 132. And it also been estimated to be around 88 petabecquerel of tellurium 132 in total. And so not just in this region, as you see. And to give some sort of example, we have the iodine releases 131 in different units, but nevertheless, you can see that tellurium is not really on the pair with iodine 131 compared to 132, but it's still noticeable at where iodine has 131 has 160 petabecquerel in total release. And as I said, tellurium has 88. Yes, and sorry for that. Yeah, so this is just to give you a sort of overview that tellurium has been released, especially during the Fukushima accident. Tellurium was also released during the Chernobyl, but it's not as relevant as for my work, as well, Fukushima had more of an intact site, and that's sort of where my research is focused on, more of an intact site where the conditions that apply there. So for this work and this presentation, there's three focuses and challenge that we want to look at, and two of the main challenges that we sort of have considered as our main aim to look at is maintaining proper cooling and preventing the release of radioactive material, which of course for cooling one potential solution could be immersion cooling, which can be used by, of course, normal water, but also seawater, which was one of the things done at Fukushima, which is sort of the first focuses of my work and this presentation. Essentially, the immersion cooling of Fukushima was done by seawater. What kind of consequences does this have? The next two topics focus comes from the next thing, preventing the release of radioactive material. So here we have several scenarios that we think of. Air ingress scenario, or if we maintain the containment, so we have more of inert or potentially reducing conditions. The two we focused on here, as the title hinted, was the tellurium interaction with cesium iodide, and the other one was with different surfaces found inside a containment, in this case BVR containment. And as to put it sort of in context to other radionuclides, we need to sort of estimate which are the important ones, and how does tellurium then stand out in the irrelevant fission product that could be released and potentially be a problem. Well, we have to look at the fission product yield of the different one, and we can see the tellurium is fairly high up. I haven't shown it here, but it is, and so it's quite noticeable produced amount in the reactor. The second thing we want to look is the volatility of tellurium, and we can see here again that tellurium is considered one of the more volatile one. So we know that tellurium is a important fission product to consider, but let's go into a bit more detail to actually specifics of them, as there is generally 4 different consideration why tellurium is an issue. And the first one, as I said, and as you saw, the volatility of it. Several of the tellurium compounds and tellurium itself has quite low melting and boiling point, which can prove to be quite problematic. Especially though they are not here, there are some organics that also have very low melting points. The next one is the decay of tellurium, which essentially all of them goes through iodine, which of course means that when tellurium decays, it forms iodine, and then anything problematic with iodine is associated with the release of tellurium. The third thing is the reactiveness of tellurium. It has actually several quirkiness, perhaps is the best word, but for example, it reacts with the cladding material, forming different species there. I will show you more of this later. It reacts with water or steam at high temperature, forming a different oxide or hydroxide, and so on, and as well as with some steels. But the biological effect of tellurium is not as critical, mainly because it's not as well documented, not researched enough, because it's quite scarce element in nature. And the only research that exists is more or less on rats. And there they observed it goes to certain organs, such as the spleen and liver. So if humans are exposed to tellurium, it's quite possible that the same organs would be affected and provide a dose to the human or the person getting tellurium inside. So, some short theory of tellurium. Essentially, as I said in the beginning, we're focusing on 2, or I hope I said, but we're focusing on 2 different conditions. Air ingress serving as the oxidizing conditions, and then we have inert conditions serving sort of inert humid, I would say. And the oxidizing sort of represent a failure of containment, reactor cooling system, but not a completely failure of the whole site. And if you look to the right, you see 2 diagrams of tellurium, phase diagrams, and you can see different species of tellurium based on thermodynamic that existed when they produced this. And you can see there is a range of tellurium compounds that can exist, and the top one is sort of dry conditions, and the bottom one is more representative of humid conditions. And the main difference is the existence of this tellurium hydroxide that can be seen in the bottom diagram. And to use this, you can see there's 2 arrows in the bottom right corner. The red one sort of represent how the tellurium in the fuel would transist around the fuel. As temperature is increased around the fuel, tellurium would proceed as the red arrow indicates. Whereas the blue shows us how tellurium would change as we get further away from the reactor core or as temperature cools down. Some relevant chemical reactions you can see here that sort of important for tellurium and sort of builds up this diagram. It can be seen to the left. And additionally, there is also the importance of tin telluride. As I mentioned, it reacts with the cladding. However, there is quite a lot of parameters for it to remain an important species. One important parameter is the oxidation potential. If it's too high, then tin tellurium will most likely dissociate. Yes, and then the second conditions I want to bring up is the one I refer to inert conditions usually. And you can see in the top right diagram, the phase diagram for tellurium under inert humid conditions. And here again, you see there is a range of different fish or species. The bottom one showing you reducing humid conditions. And some important reactions for inert conditions can be seen here and here. Oh, yes, sorry. And this too is quite important and explains the formation of oxide, for example. Otherwise, which is an important topic for this presentation, the cesium. Tellurium can also react under cesium telluride, and this is more probable during oxidizing condition, as you can see here. Or in this case, you can see that water will likely react, but it's also not very stable in oxygen conditions or at too high temperature. So, and again, tin telluride is a possibility, and in this case, much more so, because now there's less likelihood for it to oxidize. And yes, and that's a short theory. So I will start going into the experimental part, and essentially I would go through 3 of them. And I will start with the seawater. And here the question that I aim to answer is, does the use of seawater as an immersion cooling for reactor enhance the tellurium volatility? And for this purpose, I use two main methods, a TGA, which is a thermometric analyzer, which essentially is a furnace with a small scale inside it, and a normal big furnace setup, or at least for me, normal. Here I explore two conditions, oxidizing inert. I use several different ratios of metallic tellurium representing tellurium and sodium chloride representing the seawater residue. So let's start with the oxidizing conditions. And here you see the TGA results. There is three different sample ratios called S1, S2, S3, and there's two references. Reference 1, which is just tellurium, and reference 2, which is only sodium chloride. I also indicated some different melting point of different relevant compounds and elements. And what we can see here, that sample the reference 1 has a slight mass increase during between 800 and 900 degrees, which none of the other sample has, which begs the question, why don't we see at least some sort of mass increase for the sample? If you look at the sodium chloride, this one would not offset any mass increase because, well, nothing will happen until very late. So to look further into this, we decided to do some furnace experiment to just see what happens at different temperatures, essentially heating up the mixture 1:1 to a temperature and then letting it cool, and then so on. And then you get this picture, which essentially shows you how the sample looks after being heated. And you have both the images with a letter, and in the TGA you have different letters corresponding to this, showing you sort of the trend as it occurs to give you sort of a hint. And we can see that they do actually quite coincide. At around D, we start to have the mass decrease of the samples, very barely, but it does. And we can see this in the sample as well, or the furnace experiment sample. And this continues until G in the furnace experiment, which is roughly just before this mass increase is observed. And here for the reference, tellurium reference, that is, which of course this is not, because this is the sample 1:1. But we can see that at this point a yellow formation is occurring of the sample. And this continues with furthermore of this yellow observing. Already at J, we do actually see a sort of mass decrease, which is roughly where we start seeing a mass decrease for, well, at least this reference one, but also most of the samples, but not for the sodium chloride reference. So based on this, we can see that something is happening. Something is sort of preventing this mass decrease from occurring, which is possibly correlated to this yellow phase forming. However, unfortunately, when I tried to analyze this, I could not really get any good speciation of it. So it is at this, well, from this result, we can only hypothesize what is occurring. And if we start looking at different compounds, we can see that there is two possible, based solely on the color, possible species that could be this yellow phase. One is a tellurium dioxide, which has, it's a very specific crystal structure that has this yellow color, and tellurium chloride, which also has this yellow color. And of these two, the only one that has a melting and boiling point below 1,000 degrees, if I don't misremember, is this tellurium chloride. At least the melting point is below. So we can have some supporting literature that it may be this tellurium chloride that has formed, that unfortunately we could never provide a species to show this. The next conditions was the inert conditions. I will just go through shortly because we didn't really see anything here, but you have the TGA result here, the same sample with the same ratios of tellurium and sodium chloride to reference. And looking at them, they follow each other very well. There is no great differences to them. So I will actually not talk too much about this, as it did not provide, well, anything of worth at this stage, besides that, well, it doesn't seem to be affecting the tellurium. So I'm gonna do a short conclusion. So what did the question to the answer were? What was it? Does the use of seawater affect the tellurium volatility? Well, yes. In the case of an air ingress scenario, and if we have a dry-out or start to lose water in the core after pumping it in, we might have an interaction with tellurium and sodium chloride left on different surfaces. However, under inert conditions, this is not as likely, as we did not see anything. However, for this part, we cannot be completely certain at the very highest temperature, as at that point, well, we could not see anything at that point. Okay, the next question, or the next focus that I talked about before, is the reactor coolant system and cesium iodide in reaction with tellurium. And here the question essentially is, does cesium iodide enhance the tellurium volatility? And here this was a collaboration with VTT. So it's, and the system we use, you can see to the right, with some indication for a small furnace, which we use to heat the precursors, the reaction where the main experiment was carried out. And then we have some measuring point, which is the filter and the liquid trap. Here we investigated two primary conditions, oxidizing, inert. We had three sub-conditions, one these being the dry, humid, and humid with cesium iodide. In all our experiment here, we used metallic tellurium as precursors, and the cesium iodide was entered into the system through a atomizer. So let's start looking at the results from this. And we will start by looking at the transported amount, the amounts we found of tellurium we found on the filters and on the trap, and the speciation. And here we can see that the filters is the big sort of darker gray bars, and we can see that the oxidizing conditions had the highest transport during humid conditions, humid oxidizing condition, which was quite lower for, bit lower for dry, but even further lower for cesium iodide when that was added, which indicates that something reduced the amount of tellurium transported. If this is the new formation of a species or due to agglomeration, we will come to a bit later. We can then look at the inert experiment, which is, well, 4, 5, 6. Sorry, I think I forgot to mention 1, 2, 3 is the oxidizing. 4, 5, 6 is the inert conditions. And here we can see, well, we can see that under dry conditions, we had the highest transported mass of tellurium, which got a bit lower during humid, which then more or less got back to this almost the same level as during the dry when we added cesium iodide, indicating that cesium iodide enhanced or at least increased the transport of tellurium to the filter. And the second thing that we look at was in the liquid trap located after the filters. However, unfortunately, in this, there were too little to draw any conclusions. As you can see there, very little. It's the small gray one that is located close to each of the big one. However, we have the speciation left here that I want to show, and we actually did see some stuff here that could show point to something. So we started with talking about the oxidizing condition, and essentially we find, as we expected, tellurium dioxide in all filters under all conditions. When we added humidity, we did find an unknown peak, which we could not identify, to it being very weak. And when we added cesium iodide to the humid oxidizing condition, we did find a species, that was tellurium trioxide. However, it was not certain, as we had another option equally possible. But we did not find any cesium compound here. And for cesium iodide, we find essentially cesium iodide on the filter. So at this stage, we have not any good explanation to why we are seeing this transported. Well, potentially in the experiment 3, the tellurium trioxide could increase the agglomeration. The next we looked at was the inert conditions. And here we have experiment 4, 5, 6. We have actually quite similar result in the sense that we have in here tellurium dioxide forming existing on all the filters, which may be due to the transportation or potentially some oxygen leaking in, which is very unlikely. The metallic tellurium is expected, as this is our precursors, and it's not really expected to change in an inert condition, at least at low temperature. However, we did find an unknown tellurium compound, which we could not identify when we added cesium iodide to the experiment, which we just couldn't identify. However, here we also found two new peaks for both, or one new peak for both cesium and iodide. Cesium, then, besides being cesium iodide, which is the same for iodine, we also find metallic cesium, which is not very likely. It's not very stable in oxygen, and iodine 2, which is also not very possible or likely due to its being quite volatile. So we have some evidence that yes, maybe this slight increase in the transport amount, at least in the inert condition, may be due to some form of new tellurium compound, potentially with cesium. However, again, we could not be certain here. The next thing we're going to look at is the online monitoring we did during the whole experiment. One part being the mass concentration, and the other one being the particle diameter. But let's start with the mass concentration. And here you see several lines to the left, which represent, again, 1, 2, 3 is the oxidizing and 4, 5, 6 is inert. For experiment 3, we do lack parts of it in the beginning due to a technical error that was sorted out during the experiment. And here we can see that the oxidizing conditions are quite similar to one another. They have this sort of big peak in the beginning, which is due to our experimental flow scheme use, essentially forcing a lot in the beginning, but then settling down to a more steady flow. Potentially, we saw a slight increase when we added cesium iodide to the mass concentration, but this may be correlated to the cesium iodide added. For inert conditions, the mass concentration was higher than under oxidizing conditions. And we see the same trend here, actually, as we did during the masses on the filters. There are similarities. We have, there are almost similarities. We have the highest mass concentration during cesium iodide, inert humid with added cesium iodide, slightly lower during dry conditions, dry inert, and quite much lower during humid inert conditions, which, if you remember, the masses on the tellurium were on the filter of tellurium was highest during dry, followed by well, experiment 6, the humid with cesium iodide, and then the lowest at just humid inert conditions. We then started to look at the size of the particles. In general, this is not so easy to see, as this is actually each line represents different time of the measurement, and what we essentially have is a decreasing particle size during the experiment, which is potentially due to this initial surge of tellurium we have in our experiments due to the flow scheme use. In experiment 1-2 for oxidizing conditions, they are slightly bigger than that under humid cesium iodide, potentially indicating a smaller particle for cesium iodide, or at least at the measuring point. For inert conditions, we have a slightly trend of bigger particles. Initially, they are much more stable for the first two, but they are quite similar in size. I think the experiment 6 has a slightly lower endpoint of the particle. So towards the end of the experiment, the particles are slightly smaller than for the other two. Okay, so thus then, what can we say about the question as, do we have an increase in the tellurium volatility due to cesium iodide? Well, yeah, under inert conditions, there was evidence found the cesium will have an increase in the tellurium transport. As we saw during the masses, both the masses on the filter showed this and the mass concentration. And we tried to identify it if it was a cesium telluride. However, we couldn't find, but we did find something unknown. Under oxygen conditions, well, it seems more of a decrease in the transport tellurium. However, we cannot say for certain why at this point. It may be chemical related or agglomeration or both. Yes, and then we're going to go to the third experiment to focus on the final one. And the question here that I wanted to answer was the surface found in a BVR in the containment. Thus, do they affect the volatility of tellurium in any way? And here you see the experimental setup used to the right, which is a furnace. And at location 5, you have the precursor of tellurium being heated, and location 6, you have the location of the different surfaces located in a row. These surfaces being aluminum, which copper and zinc, where you can find them or where they are expected in the containment. You can see on the slide, copper coming from is expected to come in older models from melted copper cables, forming aerosols and then depositing on these surfaces. The 3 main conditions explored here was oxidizing, inert, reducing. All 3 with and without humid. So let's start, and I will only talk about the first 2. Or mainly I will talk about the first 2, or actually the first one, but anyway. So we start by looking at oxidizing condition, and to give you a sort of view, I have provided one picture, an example of the zinc surfaces before and after it was exposed to tellurium in this experiment. And in general, all of the surfaces was covered in this white layer, so there was no great big differences here. And it did not very much attach to the surface at all. It was just essentially like a very, it was a fine layer on the surface. However, I wanted to explore what it was inside of this. I want to take the speciation, I wanted the element, the morphology, and so on. So I started the process of analyzing this. And I will start by showing you the SEM image in EDX, or SEM. And here you see for the different surfaces an example of a SEM or micrographs that I produced of this deposit. Essentially, I had to remove the deposit from the surface of this because the SEM was higher. Well, it was vacuum, so I could not just put it inside as it was. So I removed it with carbon tape. And essentially, what I found was tellurium, and occasionally with most times with oxygen, which is quite expected. However, for the zinc surface under humid conditions, then I did find something, and that was zinc. So some zinc got loose from the surface of the zinc, that is. So the next step was to analyze this, and I wanted to observe what did I have on the surface, what species. So I did glancing angle X-ray diffraction. And that produced, well, it just showed that I had tellurium dioxide on my metal surface, no zinc-related compound. And for humid condition, an alternative crystal structure came, which is, according to literature, possible if you consider that we do have a sort of transient tellurium hydroxide existing under these conditions, formed between tellurium dioxide and water. Looking at the filters that I used in this experiment, I found both crystals under both conditions, meaning that there might be some other reason why this different crystal structure appeared on the surface of all the humid conditions, or the surface on all the surfaces from the humid oxidizing conditions. However, what is important to notice here, I did not find any zinc compounds. So the next step was to look at the liquid traps that I had to capture any outgoing gases. And when I started looking into that, I actually did find quite a lot of zinc. So just to make sure that this was not due to the conditions itself, I decided to do reference cases where I found no zinc. So at this point, I could not provide any real speciation of the zinc compound or why, but I could conclude that tellurium is involved in this somehow. It's just a matter of, well, continuing this research. The next conditions was inert and reducing. And the experiment, the result here again is a bit, as for the seawater one, it's not too much to say. It's quite same for all of these conditions. And the surface looked like, as you see on the example here, with the zinc again, just a thin black layer. I investigated the content for my the shapes and also the element. I found, well, rectangular spheres, spikes in all of this, so not much different from inert or reducing. The main element was tellurium with some oxygen in some location, which most likely is due to some sample or transport of the sample, and then it's probably some oxygen coming in there. I determined the speciation of this deposit, and I found tellurium metallic, and I also found that in the filters for both inert and reducing, with both humid and without humidity. So no, and the same for the liquid trap was analyzed, and here I only found tellurium. So in these cases, very little was observed. So then, if we go back to the question, does surface inside a BVR container affect the volatility of tellurium? Well, in the case of the zinc surface, it looks like that it was affected by tellurium, as it was observed that some zinc left the surface. And remember now, this zinc has to first leave a very fine, a piece of zinc going through a filter, going to some tube, and then ending up in a liquid trap. However, if this enhanced the release of tellurium or not, the volatility of it, it cannot be said at this point, because we only see the effect of zinc. So to conclude, yes, zinc will affect tellurium. However, how is not certain, if that is enhancing it or enhancing the volatility or not. Okay, so I'm just going to give you a short summary, and we're going to start with oxidizing conditions, where we saw the seawater will enhance the volatility of tellurium, at least the residue of it. Cesium iodide will likely decrease it, potentially due to agglomeration in our case, but our result indicates a decrease. Inside from the BVR surfaces, zinc will be susceptible towards tellurium. However, we cannot say how this affects tellurium, if it enhances it or not, or if it decreases it. Under inert conditions, seawater will not have a noticeable effect. Potentially, however, we cannot exclude a high temperature reaction. The effect of cesium iodide was observed, and we saw an increase or enhancement in the source term. Potentially, also new tellurium species was formed, even though we could not identify them. For the surfaces, well, no indication of any reaction between tellurium and all of the surfaces. Of course, it should be noted that this is at room temperature. So I'm gonna end essentially what more can be done. Well, there's of course continuing with the iodine, cesium iodide, tellurium, trying to identify what has formed, potentially with a better capturing process. Working with different atmospheres is also quite interesting in this case, especially with organics. Organic is quite important. Organic tellurium can be quite important in accident scenarios. And the sump, of course, is quite interesting, which of course we already started at Chalmers, through which of course Anna-Lena will talk to you about more. But yes, especially zinc in the sump would be interesting. I noticed from some other experiments, which I could not finish. Okay, I think that was it. Yes, thank you for listening. And here you see some funding agencies to the left and some collaboration with different university and institutes to the right. Thank you.
Thank you, Fredrik. We are running a little bit behind on time, so I will withdraw the question I had asked in the chat about how time-consuming your experiments have been. We will move right on to Anna-Lena Pasi, who is a current PhD student at nuclear chemistry, and she published her licentiate thesis last October, which means that she's half a PhD by now. And I hope she's ready to tell us about tellurium's behavior in the liquid phases of the containment. So I hope you're ready to share your presentation, Anna-Lena.
Yes. Hello, everyone. Can you hear me?
We hear you.
Yes. All right. And you'll see my presentation, I guess. So
Actually, a little time lag, yes.
Oh, it's good. So my name is Anna Pasi. I am from Finland, and I'm the current PhD student at Chalmers in the severe accident group. We both worked with tellurium with Fredrik. Fredrik focused on the behavior in the gas phase more, and I'm focusing on the liquid phases in the containment. And it will become a bit more clear what the liquid phases are that I've been focusing on in the past 2.5, 3 years that I've been working on this. The content, there will be a bit of overlapping with Fredrik's presentation, but I will be short with those that you've already heard. But usually we encounter the question, why tellurium? I will try to give a few points why tellurium is important. And then I'll go a bit through the chemistry of tellurium that will help to explain my results. Then we'll go to the focus of my work. And I will present the experimental section and 2 experiments that I've done related to the containment spray system and the containment sump. And those are the 2 liquid phases that I focus on. And then in the end, I will conclude the results and what can we learn from these results. So answering the question, why tellurium? We all know that iodine is the one receiving most attention, or the radionuclide that has received the most attention in the past. But why tellurium? It has several radioactive isotopes with half-lives that are relatively long to consider in the first, let's say, few days to a few weeks after an accident. Then tellurium also decays. Many of the tellurium isotopes decay to iodine, and therefore tellurium will affect also the iodine source term later on. And as Fredrik also pointed out, it is chemically somewhat toxic, has some possible biological effects. However, when we talk about severe nuclear accidents, we're more interested in the radioactivity than the actual chemical toxicity, since the amount of tellurium that a person must inhale or take in to be poisoned by tellurium is quite high. So Fredrik again also showed some numbers, but I want to also put tellurium in the context. Why is it important related to the more or the significant radionuclides, for example, iodine and cesium? We can see here on the table the releases from the 2 severe accidents, and the main tellurium isotopes are the 132 and 129 metastate. You can see for the 132 that is released in high activities, has a half-life of around 3 days. So that's that can contribute to the dose in the first, let's say, 2-3 weeks after an accident. For the 129 metastate, it has a 33-day half-life, so will stay longer in case it's released. But you can see that the activities are of the same magnitude as they are for cesium and iodine. So what do we know about tellurium in accident conditions? There's been research in the past for a couple of decades, and that has found out that the release of tellurium is delayed by interactions with zirconium in the cladding. So compared to iodine and cesium, for example, the tellurium is stuck in the cladding until the cladding is sufficiently oxidized or it melts, and before the tellurium can actually be released from the core and the cladding. The speciation of tellurium is highly affected by the prevailing conditions. For example, temperature, whether we have steam in the system, are the conditions reducing or oxidizing? And in the table here, you can see some species that are possible to be released. We have elemental tellurium in reducing conditions. In oxidizing conditions, we have different tellurium oxides. And as Fredrik also mentioned, cesium telluride, tin telluride are also compounds that have been found to form in previous research. And where my research comes to play is the liquid chemistry of tellurium. And so far, the information has been taken from geological studies, but that's not very analogous to the severe accident scenario. And you will see a bit later why. But the chemistry of tellurium in liquid phases is quite complex. And why? Tellurium can appear in different oxidation states from -2 to +6. And it has a low solubility, and this is usually what's been said on the severe accident related articles, that, well, tellurium shouldn't be an issue because it has a low solubility and it will just precipitate on the bottom of the sump. But however, the pH, the solubility increases in extreme pH values, so going to lower and higher pH. And for example, since the pH of the sump is targeted to be alkaline even around 8-9, we can assume that there's more tellurium possibly dissolved in the sump. And these oxidation states also lead to the fact that tellurium can take part in different redox reactions. And what I've been focused on is the water radiolysis product. So whether irradiation has an effect on tellurium redox reactions, because the water radiolysis produces both oxidizing and reducing species, such as the hydroxyl radical or solvated electron. And this all leads to this very complex speciation, which we can see here. Don't worry, we're not going to go too deep into this, but you'll see that depending on the pH and the potential, there's several different tellurium species that are possible in liquid phases. And therefore it's difficult to predict what in which conditions tellurium is and in which speciation. So then we go to the focus of my work. And as I already said, the two liquid phases that I've been focusing on are the containment spray system and the removal of tellurium by the containment spray system, and the behavior of tellurium in the containment sump. And these two are related since the spray that is sprayed in the containment will end up in the sump. So first we go over the containment spray system experiments. These were done at the VTT in Finland. And our focus was on the removal efficiency towards tellurium species formed under various conditions, and whether the chemical composition of the spray has an effect on the removal. And here we can see the experimental setup. So basically, we had a furnace where a tellurium precursor was heated, and the flow and the aerosols that were formed were flushed in a containment model unit that had a spray system on top. The samples we collected were aerosols that came out from the containment unit without a spray and with a spray, and we compared those results to calculate the removal efficiency. We also collected the sump. We collected a liquid trap that trapped the possible gaseous species that came out from the containment unit. And we also analyzed what happened to the tellurium precursor before and after the experiment. And these various conditions or parameters we changed were temperature, depending on the tellurium precursor, atmosphere, we use oxidizing and inert, so air and nitrogen. And we also tested whether humidity has an effect on the removal, basically on the aerosols forming. And lastly, we tested the addition of cesium iodine and whether it had an effect. And about the sprays, we used 3 different ones: water, alkaline borate solution with and without sodium thiosulfate. And these were chosen to represent different types of conditions that are used in different power plants. Going on to the results, first, if we look at what went into our system. This is the particle size distribution of the different experiments. In general, we can say that the diameter of the tellurium aerosols was less than 1 micrometer. However, larger agglomerates were formed, and that's why the distribution extended to several micrometers. As I said, we tested whether cesium has some sort of an effect. And with the cesium iodide, we saw larger agglomeration. So we saw larger particles, and therefore the distribution also grew wider in these 3 experiments. And then lastly, I want to point out the line on the bottom here, which is experiment 5. We had a very low low formation of any aerosols, and we also saw some inconclusive results with the other samples we collected, and therefore we suspected an experimental error, that something went wrong during that experiment. And if we look at the tellurium releases, here I want to point out, so these are the mass of the precursor before and after the experiment, how much mass was lost from the crucible. And here I want to point out these 3 experiments, 4, 5, and 6. And these were done with metallic tellurium in air atmosphere. And you can see that the mass loss was very low or small, or even we had a slight increase. And we suspected that possibly tellurium, the metallic tellurium precursor had oxidized, since we had air going into the system. And this was also investigated with X-ray diffraction, and it was confirmed that oxidation had happened. So these results are here to, we analyzed all these samples in order to possibly explain some differences in the removal efficiencies, which I can show here. So as I said, we collected filters. For every spray experiment, we had a reference filter that was collected without any spray on. So we knew in those conditions how much aerosols is going through the system. And those are the first 3 bars in each graph. And then we compared those to the spray conditions. But I think it will be easier to look at the actual removal efficiency percentages. So generally overall, the removal efficiencies were quite high, reaching almost 100%, 99% removal efficiency. However, there are some differences. As you see, experiment 5, as I said before, that we suspected an error. And there we, compared to the other experiments done in air atmosphere, the removal efficiencies are low, and also the formation of aerosols was low. So those results are inconclusive. And then the other point is the last 3 experiment done with tellurium metal in nitrogen atmosphere. There, the removal efficiencies were generally lower, as low as 60%. And we suspected that it might have something to do with having different sized particles that are, or aerosols that are not efficiently removed by the spray. However, we can't exclude some sort of a chemical effect. Going on to the other liquid phase, which is the containment sump. And there the question was that, does irradiation have an effect on tellurium chemistry? And if yes, what happens to the tellurium speciation? And does the chemical composition of the sump have an effect on the speciation? And here on the left, you can see the sump solution I used. It was actually the same one we used in the spray. And the sump, in general, it is a very complex mixture of chemicals and components. So this is a very simplified system. However, So the two parameters that were changed were whether a sample was irradiated and whether it had sodium thiosulfate in the samples. So every irradiated sample had a corresponding reference sample. So first, if we look at the solubility results over time, and time here is either time for the reference samples or irradiation time. And 3 points from here is that in the solution where no thiosulfate was present, the solubility of tellurium increased with longer irradiation times, which is the blue line. When we had thiosulfate in the system, the solubility decreased with longer irradiation times, and that's the orange line on the bottom. And then lastly, both of these reference samples, so in both solutions, the solubility reached an equilibrium at around 16 millimoles, which is a literature value also for tellurium solubility. So already here we can say that it seems that irradiation has an effect and it depends on the solution composition. So I started looking at the speciation. First, I looked at what was left in the solid material. I had an excess of tellurium dioxide in the sample, and I dried and ground them and measured with XRD. Here's what the sample looked in the reference sample and in the solution with sodium thiosulfate that was irradiated. So reference sample was found to be only pure tellurium dioxide, which was put in the sample in the first place. And when the sample had been in the gamma cell and irradiated, the mixture was found to be metallic tellurium and tellurium dioxide. So some of the tellurium dioxide had reduced to metallic tellurium. And this would explain also the decrease in solubility, since the metallic tellurium is very insoluble in any liquid phase. So looking at liquid speciation, I used ion chromatography, which basically separates the components in the liquid, and we can identify them with their different retention times. They look something like this. So the peaks A and B are from the solution matrix itself, from the sodium hydroxide and borate, but the C is the sample that was irradiated without sodium thiosulfate. And as we saw in the solubility graph, the solubility increased. And here we can see that the tellurium species that was in the sample after irradiation was a tellurium 6 species. So tellurium had oxidized from this tellurium dioxide to a tellurium 6 species, which is more soluble than the tellurium dioxide. So we can suspect that tellurium has reacted with these water radiolysis products to produce this oxidized species that is more soluble. And in the solution where we had sodium thiosulfate, whatever tellurium was left in the solution was just dissolved tellurium dioxide in the oxidation state 4. So here, this is the what happened to the actual solution, some solution under irradiation. We can see bottom here is the solution before, and the red one on the top is how it looked after irradiation. And a couple of points here, the thiosulfate oxidized to sulfate, and this is known from the literature to happen according to this reaction. So there's no surprises there. But what was interesting was this area between 2 and 6 minutes, and that's where was peaks for the borate. And we can see some possible changes in the borate speciations that cannot be identified, and maybe that's something for the future. So then, looking at what happens to tellurium dioxide under irradiation. When we don't have sodium thiosulfate present, so we have alkaline borate solution, It seems that tellurium is dissolved and reacts with the oxidizing water radiolysis products to produce a more soluble species, tellurium-6. And maybe what is left are the reducing species that maybe change the speciation of the borate, but that couldn't be concluded. And when we have this thiosulfate present, we saw that the thiosulfate comes to oxidize, so that will take up all the oxidizing species, and what is left for tellurium to react are the reducing ones, and therefore we see the reduction of tellurium to the metallic tellurium state. So what can we learn from these results? There's a lot of chemistry, a lot of basic research involved. What can we say? So the containment spray system seems to be efficient in removing tellurium species. When we had cesium iodide in the system, the removal was somewhat increased due to larger agglomeration. And as in the removal in the inert atmosphere, so with nitrogen, it was slightly lower, however, up to 60% still. And we couldn't really see any significant effect on the chemical composition of the spray, whether it was just plain water or some chemical composition. And then it seems that the radiation has a significant effect on the tellurium behavior in the containment sump, both in increasing and decreasing manner depending on the solution composition. So the solubility increased due to oxidation when we didn't have sodium thiosulfate. When we had it, the solubility decreased due to reduction of tellurium dioxide. And this all leads to what is interesting is that when we have more tellurium dissolved in the sump, that can take part in further reactions with other fission products, or for example, organic material, and form more volatile species. And that's actually something that I'm looking into now. What is the possible formation and even pre-volatilization of organic tellurides in the sump? Whether we have interactions between tellurium and iodine, it has been suggested in literature, but there hasn't been any experimental data shown yet. And then, as I said, the borate speciation was interesting, what happened to it under radiation. And maybe that's something for the future to research. And I would like to thank you for your attention, and thank you for all the partners and collaborators. Yes.
Okay, thank you, Anna-Elina. We will take one quick question from the chat, and then we will go for a short break so that we can be back for the concluding session 3 at 2:30. And it's a question from Henrik Glenneskog, and he asks if you know if the speciation of tellurium compounds found in the environment around Fukushima has been investigated. Do you know that?
Well, I don't know about the speciation. I know that the environmental sampling was done after the Fukushima. The soil samples were collected, water samples were collected, but then I wouldn't say that the same speciation inside the containment is the one that possibly stays in the environment, because it has it reacts so easily due to the different oxidation states. And the 4 and the 6 are the more prominent in environmental conditions. So it's hard to say whether those are the same that are in the containment.
Yes, of course. Thank you.
Thank you.
Okay, so that concludes session 2, and now we can all go for a short 10-minute break and be back at 2:30 when we will begin the concluding and a bit shorter session 3. See you in a bit.
Hello, everybody. We start session 3 for Apri seminar. And my name is Gennady Loskotov, and I work for Swedish Radiation Safety Authority. We have just one presentation in our session. It's about ROAM, and this is methodology for dealing with uncertainties when you need to make a decision based on some numerical results, and I think it's very interesting. So I gave a word direct to Pavel Kudinov, who will present the methodology.
Thank you very much. Can you see it and hear me? Okay. So I will speak about the risk-oriented accident analysis methodology and our work, which has been done in Apri 10 with regards to in this area. So you have seen already this picture. Just to remind that we are looking at the threats to containment integrity, ex-vessel steam explosion, and formation of non-coolable debris bed. And this basically management strategy, which implies fragmentation of melt in a deep water pool and formation of coolable debris bed, is conceptually simple, but it also introduces complex interactions between a large number of phenomena and also accident scenarios. And this complexity, because of those interactions, limits heuristic approaches in the problem decomposition and a priori judgment about importance of different factors. We need an adequately systematic approach in order to actually assess effectiveness of the strategy and the risk of containment failure. So risk-oriented accident analysis methodology was developed originally by Professor Theophanes in the United States, and it marries those probabilistic and deterministic approaches. And it is designed to address the issues where both scenario and epistemic phenomenological uncertainties are significant. So in Apri 10, we rely on significant progress that has been achieved in ROM Plus development in Apri 8 and Apri 9. And the main goal for the Apri 10 project was to support the deployment of the risk-oriented accident analysis methodology framework, ROM Plus. And main task was to deliver a prototype code package, which would implement current version of ROM Plus and can be used independently by the end users. And we organized a couple of workshops where all who were interested were able to actually train a little bit in how to use this code. Few words about the ROM Plus itself. So in addition to ROM, classical ROM, it involves two aspects. One is the extended treatment of safety goals. So in classical ROMs, we only look at the possibility of containment failure, and we try to demonstrate that failure probability is less than some screening probability, which corresponds to physically impossible level, physically unreasonable level. But in ROM Plus, we also look at the other question, whether or not we actually need to modify severe accident management strategy. And that would be needed if necessity of containment failure, or in other words, possibility that containment will not fail, is actually high. So in this case, the failure probability is larger than 0.999. So we look at these both questions and try to provide background information for such decision. And decision is considered as robust if it is insensitive to the remaining uncertainty. Also, a few words before we proceed to just remind about the risk quantification. So we consider risk as a triplet, where important factors are scenario, frequency of this scenario, and consequences. or more precisely, likelihood of certain consequences. And those likelihoods of consequences usually are a result of some modeling, so predictions, and this involves the epistemic knowledge uncertainty, so in our ability to predict what will happen. There is more general definition where frequency itself becomes a distribution, and the probability again is not just one number but a distribution of probabilities for the consequences. In any case, the separation, such separation of epistemic and aleatory stochastic uncertainties are important element and one of the cornerstones of the classical ROM and ROM+. In ROM, modeling parameters, those epistemic uncertainties, are separated in two major groups. One is so-called deterministic parameters, which for which we have complete probabilistic knowledge, which means that we know about the ranges and probability distributions. And then intangible parameters for which we have only partial probabilistic knowledge. For instance, we can speculate about the possible ranges of those intangible parameters, but we cannot say much about their distributions. In ROM+, we assess the effect of this missing information about the distributions of the intangible parameters on the result. And how we do it, so if we have a model or causal relations and we have input into this model, which comes from prediction, for instance, of a certain plant damage state, and then we have intangible parameters, which are internal modeling parameters in this model. And we generally don't have those parameters, distributions of those parameters. But if we have just one distribution, if we assume one distribution of this parameter, then we will have a distribution of the output, which can be expressed in terms of load and capacity in general case. And this load and capacity can give us the failure probability. Right, so one distribution of intangible parameters gives us one value of the failure probability. Now, we don't know actually about this distribution, so what we have to do is actually assume that they can be any. So we start sampling from some family of possible distributions, and each time we take a new possible distribution from this family, we get a new distribution of the output, and this new distribution of the output gives us new value of the failure probability. Eventually what we have is a distribution of failure probability, which reflects the effect of the uncertainty in the distributions of our intangible parameters. Now, this, what I said, was just for one point for the model input. So for the same point, let's say that it was combination of certain jet radius and the water pool temperature. And we would get a distribution of failure probability like this. But if we change this combination of the input, then we will have different respective distributions of the failure probability. And in order to represent them in a compact manner, what we do, we color code them. And we say that green domain is where failure probability is at most in 5% cases larger than the screening. In red, failure probability is larger than the screening one in at least 95%. And then blue and purple is kind of transition, which means between 5 and 50 in blue, and purple from 50 to 95. So this gives an idea about so-called failure domain and distribution of failure probability and its uncertainty in the space of the model input parameter. Important for ROM+ is actually process in which we identify what are the important parameters and what has to be done in order to actually quantify the uncertainty. And it starts with calculating the failure probability, like just we discussed, some integral failure probabilities. Now, if the results are inconclusive, for instance, if possibility of failure is high but necessity is low, then we need more knowledge. And then we proceed to step 2, where we do sensitivity analysis to identify those more major contributors to the current uncertainty in the models. We build failure domains, just as we discussed, in the space of those identified most influential parameters, in order to understand which combinations of those parameters can lead to failure. And that gives us an idea where we need refinement of knowledge, where we need to gather more information, maybe do more experiments or develop new models. As I mentioned, the ROAM Plus was implemented as a code, which actually implements all the important stages of the analysis, including the surrogate model coupling between themselves, sensitivity analysis, quantification of probability of failure, and visualization of the results. And also it has export for external tools such as PSA software, and I will come back to this later on. So this is what is more or less implemented in the current version, where we have the top layer of ROAM framework, which decomposes severe accident progression into a set of causal relations, each represented by a surrogate model. And all the information is propagated from
Pavel, if you hear me, that we lost the sound from your presentation. Okay, we have no sound right now, so hopefully we can try to find the reason for that and fix the presentation. So stay online. hello everybody again, and hopefully we fix the problem now. There a technical problem with sound feed, and Pavel will start at where we have lost the sound, and it will be the slide 15, I think. So sorry for the interruption, and stay with us. We are still going, and now hopefully the problem is solved. So Pavel, again, you can start with slide 15 and forward. We have time for your presentation. Thank you.
Thank you. Sorry for that. So I will try to speed up. So this is the top level of the framework, which consists of the surrogate models, which are important for computational efficiency. And those surrogate models are based on full models, which are very detailed descriptions of the physical phenomena that are important. And there is a process how to actually obtain a reliable surrogate model, which reflects important output of the full model. There is a large number of publications for each surrogate model, and you can track and look at the details how it was obtained and what were the assumptions. I direct you to the Apri report for those details. Here we look only at steam explosion and debris coolability surrogate models and their final application. So I will not go in discussion how those surrogate models were developed. So same is steam explosion surrogate model, which is based on Texas 5 code. We consider two fragility limits. One original design with 6 kilopascal limit or non-reinforced hedge door, and another one modified design with reinforced hedge door, which can sustain up to 50 kilopascal second limit. Now, surrogate model has an input which includes pool conditions, jet properties, and some internal Texas modeling parameters. And if all of them are sampled as intangible parameters, then we have a distribution of failure probability, which is shown here for respectively two options for 6 kilopascal and 50 kilopascal second. And you can see that possibility of failure is actually quite large, and our failure probability exceeds the screening 10⁻³ in more than 99% cases. If we consider non-reinforced door, and modified reinforced door improves the situation slightly, so we exceed this screening probability in 70% of the cases. However, if you look at the necessity of failure, then it's actually low. So only in 6% we exceed the 0.99, and only in 0.3% for the reinforced case. So when possibility of failure is large but necessity is relatively small, we need further knowledge, or basically system modification. But first we look at further knowledge which can be obtained at the level of the melt release. And if we look at the sensitivity analysis results shown here, this is a typical Morris diagram where parameters which appear in this corner are the most important. So here we can see those radius of the jet, temperature of the molten fuel, and the water pool depths are the most parameters. And actually all other parameters are less important and significantly because it's a logarithmic scale. So even if we know more about those parameters, we have no significant effect on the risk assessment results. Now, if we look at the failure domain analysis, so in this case, we take the those most important parameters, radius of the jet and fuel, as the input parameter to the model, and then build the CDF of failure probability for each combination of these parameters. We can see these kind of pictures where we can see clearly a large red domain for the non-reinforced case, and basically we can say that the possibility of failure can be low only for very low values, about 5 centimeter of radius of the jet radius. And if we reinforce the door, then we can consider that this failure is physically unreasonable for jets which are larger, up to 175 millimeters in radius. If we look at the necessity of failure, then this means that we are setting screening probability to 0.999. And for the original design, we have this size of the domain, so-called safe domain. But what we are looking for mostly is where the failure is unavoidable, and it appears to be unavoidable for jet radiuses larger than about 20 centimeters. And even for reinforced case, if jet radius is larger than 25 centimeters, failure probability exceeds screening one in more than 5% cases. So this suggests that really effectiveness of severe accident management completely depends on the uncertainty in the melt release conditions. The same process can be done with debris collability. So we have debris collability surrogate model, which is based on full model, which is the Casim code. And we take into account the effect of agglomerates on the collability in the Casim code and the respective surrogate model. We also introduce different failure criteria such as coolable or no dry out criterion for collability of debris bed, and then a set of criteria which are based on different temperature limits. So if temperature can be stabilized below certain limits, we still consider that debris bed is coolable. There is a list of input parameters to the surrogate model, and if we sample them according to the process that we discussed above, we will get results like this. So the red line is the failure probability based on the dryout criterion, and then all other criteria based on different temperatures actually give very similar distributions of failure probability. So actually absolute values are not so important here. So what we can see is that failure probability is larger than 10 power minus 3 in approximately 99% of all cases. And it's larger failure probability than 0.999 in approximately 47% for the criterion based on the dryout, and about 25% for different temperatures. So the necessity of containment failure due to ex-vessel debris collability is high, but maybe not sufficiently high to claim that the failure is completely unavoidable. And the failure we can say from the sensitivity analysis results and the same type of Morris diagrams is mostly affected by the pool depths and the melt release conditions, which include the jet size, velocity, and temperature. So then next step, of course, is to obtain this information about the melt release conditions. And for that, we develop surrogate model for melt release based on melt core analysis. And we consider a station blackout scenario with and without depressurization. and different mechanisms of the vessel failure, specifically penetrations and gross failure of the wall. And those are not mutually exclusive, which means that one can happen and the other can happen. The really important element of this of the model, which includes many internal parameters in Melcore, but one which turned out really important, and we show how important, is this modeling of the melt ejection condition from the vessel. So if we set so-called IDG parameter to 0, which means that we allow both liquid and solid debris ejection, or if we set it to 1, then we allow only liquid melt ejection, and this changes completely the behavior and the risk assessment results. Hello, can you hear me?
Yes.
Yeah, okay. So now this slide shows results of Melcore analysis with respectively variation of many different parameters. And for two cases, this IDG 0, which means solid debris ejection is possible, and only liquid debris ejection. And you can see that if we have solid and liquid debris ejection, then we have typically gradual melt relocation. This is debris mass ejected from the vessel. And in case when we have only liquid debris that can be ejected, then we have accumulation of large mass of melt and then massive release. And because there is no real data to suggest which mode is, let's say, more adequate description of the reality, so we have to consider all those as splinters. And splinters are those phenomenological scenarios where epistemic uncertainty is beyond the reach of any reasonably verifiable quantification. So we introduce the splinters where we consider the possibility of failure about 25% of instrumentation guide tubes in each wing modeled by Melcore, or 100% of those tubes, and then respectively either only liquid or solid and liquid debris ejection. So all those are considered as independent branches of analysis. And this is just to show that the surrogate model can reproduce Melcore prediction for different parameters, in this case the radius of the jet, which was shown as one of the most important parameters in sensitivity analysis. So now when we have separate models, separate surrogate models for melt ejection and steam exposure and coolability, we can start coupling them and doing coupling analysis. So those, this is the result, and they are grouped. You can see here in red, we have lines for original design with 6 kilopascal second, and blue as 50 kilopascal second. Which means modified reinforced design. And then each plot corresponds to either basically IDG1 or IDG0. So for instance, here you can see the distributions which are summarized here in terms of the expected value. And you can see that in case when we have IDG0, failure probability generally exceeds screening probability in about 17–23%. But if we have only liquid melt ejection, then we exceed it in 100% for original design. If the door is reinforced, then again, for the solid and liquid debris, we actually have pretty close to 0 numbers, which means that this would be a reliable strategy. But if only liquid debris can be ejected from the vessel, then the probability of failure is actually quite high. And the same can be seen, the same effect of the IgG can be seen on the necessity of failure. So necessity is low when IgG is 0 and is high for the original design, but actually it becomes low for modified design. So let's say by making this modification, we can actually avoid high certainty in the failure of the H door due to steam explosion. And these two plots, by the way, they provide kind of idea about the importance of how many IGTs are failing simultaneously in each ring. Now the same can be done for the debris coolability. So these are the overall failure probabilities obtained with solid debris ejection on and solid debris ejection off. And again, you can see here that in most of the cases we exceed actually failure probability exceeds the screening probability, and actually even larger than 10 power minus 1 in maybe 90% cases. The same type of sensitivity analysis can be done, and we can see actually that the pool depth becomes really important parameter for coolability for all different configurations. And there are some additional parameters like initial debris slope angle that can be also important, for instance, for dry out based failure criteria. Now, coupling with PSA. So once we have done this type of analysis, we have the distributions of failure probabilities for each phenomenon that can threaten containment integrity, for instance, steam explosion and coolable or non-coolable debris bed. And actually, those distributions can be used in PSA analysis in some software. Like risk spectrum, which allows to take into account the distribution of failure of probabilities in the PSA analysis. And these are basically types of distributions which we provide for different combinations. Let's say deep pool, shallow pool. They can be obtained using the ROAM Plus framework. So this is quite flexible. I mean, connection between how the events, containment event trees are represented in the PSA, and then respectively you can obtain those distributions of failure probabilities in ROAM Plus. And this is a summary comparison. And again, those are two results. One is for solid debris ejection off and solid debris ejection on. And this is a comparison which is normalized frequency of so-called non-contained release. So we group actually here both the melt penetration, basement melt through cases and the steam explosion cases together, because both of them can lead to large offsite consequences, although according to industry practice, current basement melt through is considered as happening late, maybe more than 72 hours. So that's why in the, let's say, state-of-the-art analysis, it's not included in the unacceptable release frequencies. So what we can see here, the reference results, just typical PSA, then results with reinforced hedge door, non-reinforced hedge door. And you can see that, for instance, if we have this solid debris ejection on, the difference actually is not significant. Sometimes you have some changes, but overall the results are pretty close to what is in the PSA currently. However, if we consider solid debris ejection off, only liquid debris ejected, then they can vary really in large range, and generally they increase. This is a summary of now all the cases. So here they are split to according to different initiating events, and here they are grouped all together. So again, you can see here IDG 0 and IDG 1, only liquid melt, significantly increased probability of failure compared to reference analysis. And here we can see some effect of door reinforcement, but it's not, let's say, dramatic, because significant fraction of failures coming from actual debris, non-coolable debris. So in conclusion, we have developed the framework, we developed the code which can be used with PSA, we have demonstrated how the process can work, and we can see that this application of PSA with ROM Plus is not only feasible, but actually could potentially lead to improvement of PSA in terms of sequence definition, and also considerable change of the frequency for non-acceptable releases. So these are details which I think I already have said, so I will stop here for the sake of time. Sorry for the technical problems on the way.
Thank you, Pavel. It was very interesting, despite of dramatic interruption. We have, I hope we have time for one question. That the calculations using ROAM, it does a lot of calculations. Is there any bottleneck in the process, and in what? And if there is some bottleneck in calculations, where it lies?
So the major time actually is needed for development of the full models. So this is what takes a lot of time, and this is a typical research process. Then, of course, some time is needed to develop and adequately validate the surrogate model, but once it's done, then you can run the RAM analysis within the order of days on a typical desktop, I mean powerful desktop, but you can run it quite effectively. So once you have already surrogate models developed, then there are no major bottlenecks. I think we had this exercises during the workshops, and everybody could run it, and it takes just minutes. It all depends, of course, on the resolution. For instance, for the failure domain, what was the resolution which you would like to see? But if you select reasonably coarse resolution, then it takes minutes, actually.
Okay, thank you very much for your answer, and I think it's a very good example when you can connect deterministic analysis with probabilistic one. So thank you again for your presentation, and I leave the word to Moritz.
Thank you.
Thank you.
Okay. Just final for today. So I would like to thank all the presenters and all the moderators for their efforts today. And a special thanks to my and Smart Media, the produced webinar today. Of course, we'll continue tomorrow. And finally, wish you all a nice day and welcome tomorrow at 10 o'clock. Okay. So, thank you very much. And as I said, have a nice evening.